now we are going to discuss another concept, which is the inverse Bode plot. What is the meaning of inverse Bode plot? Means just by seeing the magnitude plot, we have to write the Oberth transfer function equation. We have to write. So up to now, what we have done from the Oberth transfer function, how to draw the Bode plot we have discussed. So inverse Bode plot means from the seeing a diagram, how to write the Oberth transfer function, that we are going to discuss. So up to now we have discussed from Oberth transfer function how to draw the Bode plot we have discussed. But now inverse Bode plot means just by seeing the Bode plot, we have to write the standard equation of the Oberth transfer function. We have to write. So very carefully, observe the starting slope. This will give the information of the poles or zeros occurring at the origin. So first thing is, from this Bode plot diagram, we have to observe the starting slope. So this will give you the information regarding the number of poles or the zeros which are going to occur at the origin. So this is the first point always you have to keep in your mind. So just by observing the starting slope of the magnitude Bode plot, we can tell the number of poles or the number of zeros which are going to occur at the origin. So now we can say, suppose if the starting slope is placed to the decimal square decade, means there is only 1 zero at origin. Suppose if there is placed for the decimal square decade, means we have 2 zeros at origin. Suppose it is a minus to the decimal square decade, means 1 pole at origin. If it is minus for the decimal square decade, means 2 poles at origin. So therefore we can say, just by observing the starting slope of the magnitude Bode plot, we can tell this number of poles or this number of zeros which are going to present at the origin. The next point is, for the starting slope line, write the equation. So write the equation. So for the starting slope line, write the equation always. So only for the starting slope line only. Always you have to write the equation, which is y is equal to mx plus c. So at a particular point. So this equation is going to hold at any point in the first line only for the first slope line. So what is the value of c? C is nothing but, so c is basically, it is always equal to 20 log k. So c is always equal to 20 log k. So c is always equal to 20 log k, and x is nothing but log omega. So x is equal to log omega and c is equal to 20 log k. So what we have to find? We have to find the value of k. So you can see x is equal to log omega, c is equal to 20 log k, and m is the slope of the initial slope line. So initial line, the slope is, we have to take here m, and y basically at a particular point get the value of y. So therefore we will get from the diagram. So from this try to get the value of k. So y is equal to mx plus c. So m is the slope of the first line, where x is equal to log omega and c is equal to 20 log k with the base 10. So base is always 10. Here base is 10 for each and everything. So for everything the base is 10 only here. So therefore you have to get the value of k. So by this way we are going to get this one. So now the next point is, at every corner frequencies, observe the change in the slopes. This will give the information of the first order or the higher order factors. Yes, at each and every corner frequency, observe the change in the slopes. So this will give the information regarding the first order or the higher order factors. So just to see here, I have already told you, at each and every corner frequencies, try to find how much amount of phase height, how much amount of slope that we are going to add to the previous graph now to get the next graph slope. So what is that value? From that we can say whether they are the first order factors or the higher order factors, we can easily obtain. And obtain the g of h of s in the standard time constant format. So what is the standard time constant format? G of s h of s. So g of s h of s is equal to k into 1 plus t1s into 1 plus, I can say, ta and then ta. So tds and goes on. Similarly here by 1 plus t capital A S, I am going to add here, into 1 plus t capital B S. So this is the standard time constant format of the open loop transfer function. So listen carefully. I have already told you inverse Bode plot is, just by seeing the Bode plot, we have to write the open loop transfer function in the standard format. How to write? First thing is, by observing the starting slope of the magnitude Bode plot, by seeing that we can say this one number of poles or this one number of zeros which are going to occur at the origin. which are going to occur at the origin. So here you have to write here basically you have to write here yes, or here also you have to write yes as the power of p, there is the power of z you have to write, there is the power of n. So as the power of p. So this is the standard time constant formula. So now the next point is for the starting slope line, always you have to write the equation which is y is equal to x plus c, where x is always equal to log omega with a base 10 and c is equal to 20 log 2 with a base 10. So at a particular value of omega, you will get the value of y from the graph. So from this get the value of k. So at every corner frequencies, observe the changing of slopes. This will give the information of the first order or the high order factors. Means at each and every corner frequencies, try to figure out how much amount of slope that you are going to have to the previous graph in order to get the next slope. So by seeing the slope, we can say which order is added, whether the 0 or 4, we can easily figure out. So by all these things, we are going to obtain the open loop transfer function g of s h of s in the standard time constant form, which is g of h of s is equal to k into s the power of z into 1 plus PIS into 1 plus TDS and goes on by s the power of p into 1 plus PIS into 1 plus TDS and goes on. So this is the standard time constant format. So just by seeing the Mandelbrot plot, we can get back the standard time constant open loop transfer function. So now listen carefully. Finally, I am going to give some summary for each and everything. Suppose I already told you for the fact that when g of h of s is equal to plus or minus k, then there is no corner frequency and the matrix plot is 20 log k with a base 10 and the slope is always equal to 0 decimal per decay. So for all the frequencies, it is having a matrix plot which is 20 log k with a base 10 and the slope is 0 dB per decade. Suppose for s the power of plus or minus n, means s is nothing but j omega. So j omega on the power of plus or minus n, then what is there is no corner frequency. So we are going to get the Mandelbrot plot and the equation is plus or minus 20 n log of omega with a base 10. So plus or minus 20 n log of omega with a base at 10. So basically at omega is equal to 1, we are going to get the dB as 0 dB that we are going to get here. So now what is the slope here, which is plus or minus 20 decimals per decade. Plus or minus 20 decimals per decade. So now for the other thing, which is 1 plus st all the power of plus or minus 1. So s is equal to j omega. So for this one, what is the corner frequency, which is we can say 1 by t. So 1 plus st, the time constant is t. So therefore the corner frequency is 1 by time constant is 1 by t. Then basically below the what is the cutoff frequency? This is the cutoff frequency, right? Corner frequency, cutoff frequency. So below this cutoff frequency, the Mandelbrot plot is 0 dB, and above this cutoff frequency, the Mandelbrot plot equation is plus or minus 20 log omega t with a base 10. Then what is the slope? Slope is nothing but plus or minus 20 decimals per decade. And for I've already told you for the s square by omega n square plus 2 zeta omega 2 zeta s by omega n plus 1 for the power of plus or minus 1. So if substitute s is equal to j omega, we are going to get 1 minus omega by omega n whole square plus j 2 zeta omega by omega n to the power of plus or minus 1. So for this, the corner frequency is omega n actual frequency itself. So below this one, the Mandelbrot plot is 0 dB, and above this one, the Mandelbrot plot equation is plus or minus 40 log of omega by omega n to the base 10. So now we can say what is the slope? Slope is nothing but here we can say plus or minus 40 decimals per decade. Plus or minus 40 decimals per decade. So these things always you have to keep in your mind. So if you remember this concept, then you can solve any of the questions in a very easy amount of manner. So finally I can repeat. For a g of h of s is equal to plus or minus k, there is no corner frequency, and the equation of the Mandelbrot plot is 20 log k with a base 10, and the slope is equal to 0 decimals per decade. For g of h of s is equal to s the power of plus or minus 1, so d plus s by j omega, we are going to get j omega all the power of plus or minus 1. There is no corner frequencies, and the amount of the Brode plot is, and the amount of the Brode plot equation is plus or minus 20 n log omega with a base 10, and the slope is equal to plus or minus 20 in decimals per decade. And for 1 plus st all the power of plus or minus 1, then it is s by j omega. So this is g of h of s. So cutoff frequency is equal to 1 by t, So below this cutoff frequency, the magnetic Bode plot equation is plus 0 dB, and above this cutoff frequency, the magnetic Bode plot equation is plus or minus 20 log omega t with a base 10, and its slope is always equal to plus or minus 20 decibels per decade. And for the at the g of h of its open loop transfer function, which is s square by omega n square plus 2 zeta s by omega n plus 1 to the power of plus or minus 1. So to s by j omega, we are going to get 1 minus omega by omega n whole square plus j 2 zeta omega by omega n whole the power of plus or minus 1, the cutoff frequency of the corner frequency, which is omega n. So below this cutoff frequency is the magnetic Bode plot equation of 0 dB, and above this cutoff frequency, corner frequency, the magnetic Bode plot equation is plus or minus 40 log omega by omega n with a base 10. So what is the slope, which is plus or minus 40 decibels per decade? So plus or minus 40 decibels per decade. So all these things always you have to keep in your mind. So if you remember this one, you can draw the any Bode plot equation, any Bode plot you can draw it very easily. So this is the concept always you have to keep in your mind. Now we are going to discuss the another concept, which is called as the state space analysis. So this is called as the state space analysis. So basically, if I take some system model, suppose if I take some system model, so these are the inputs and these are the outputs. So here, let me assume there are u number of inputs and there are y number of outputs. And there are state variables are, let me assume there are x state variables. So we can say for this given system model, there are u inputs and y outputs, and there are n x state variables. Then what is the state model equation? Which is basically x of t is equal to a into x of t plus b into u of t, whereas y of t is equal to c into x of t plus d into u of t. So this point always you have to keep in your mind. So this is called the state equation, and this is called as output equation. So overall this is called as the state model equations. So we can say x dot of t is equal to a into x of t plus b into u of t, whereas y of t is equal to c into x of t plus d into u of t. This is called as the state equation, and this is called as the output equation. So overall this is called as the state model equation. So basically there are multiple inputs and there are multiple outputs, and there are x state variables. State variable space, these are the variables which are basically, suppose the current in the inductor is a state variable and the voltage of the capacitor is also a state variable. So these things always you have to keep in your mind. So therefore we can say for a given system model, if there are u inputs and there are y outputs and there are x state variables, then x dot of t is equal to a into x of t plus b into u of t. So this is called as the state equation, and y of t is equal to c into x of t plus d into u of t. So this is called as the output equation. So overall this is called as the state model equation. So now the next concept is figuring out the system model from the differential equation or the Laplace transform. So figuring out the system model from the differential equation or the transfer function. So how to figure out the system model from the differential equation or the transfer function? How to get this one? So that is what we are going to discuss. So listen carefully. Output itself is taken as the one of the state variable. So in this, output itself is taken as one of the state variable, and the number of state variables is always equal to the order of the system, and the matrix A is said to be the Bush form or the companion form. So the matrix A is said to be Bush form or the companion form. So we can say the output cell itself is taken as one of the state variables. So therefore number of state variables is always equal to the order of the system, and the matrix A is basically called as the Bush or the companion form. So we can say that the output itself is taken one of the state variable, and the number of state variables is always equal to the order of the system, and the matrix A is basically, it is said to be Bush form or the companion form. Suppose there is some transfer function y of s by u of s, where y of s is the Laplace transform of output and u of s is the Laplace transform of input, which is equal to as plus b by s square plus ps plus 2. So we can say for this transfer function, the characteristic equation is s square plus ps plus 2, and the order is, we can say, second order. The characteristic equation is having the order of 2. So I can write like this, I can write this one in other format, which is 1 by s square plus ps plus 2 into as plus b. I can write like this one, so therefore as plus b. So now what I will do, basically, if you see, the order of the equation is equal to 2, so the order of the equation is equal to 2, so therefore we can say it is basically a two-state variable, because the order of the system is equal to, so number of state variables are 2, so therefore x1 dot x2 dot. So this is A. This is x1 x2 plus b into u, and y is equal to c into x plus d into u. So d is always equal to 0 in this case. So d is always equal to 0 into u of t. So therefore this matrix is always equal to 0. So now, if you listen carefully, how to fill this matrix, how to fill this state equation, state model equation. Let me see here. So these are two state variables, right? Because order system is equal to x1 dot x2 dot a into x1 x2 plus b into u of t, or y of t is equal to c into x of t plus d is nothing but always equal to 0 in this Bush companion form, 0 into u of t. So now, listen carefully. So now you have to go from here left to right. So you have to go from left to right. So here you have to go from left to right. So if you are going from left to right, here it is a Q, here it is a P. So write in the reverse fashion, means write with the negative sign. So minus Q, minus P. And this one is, the upper one is always 1. Then 0, again 1, again 0, again 1, again 0, like this. So listen carefully. Suppose if you take here minus 2, minus P, suppose minus R, everything like this. So this is always equal to 1. Then this is 0. Then this is 1. So again, this is fifteen remaining with 0. So like this 1, you can see here, this is 1, 0, 1, 0, 1, 0. Like this, you have to go for a staircase. So this is about the minus 2, minus P. This is 1 means the remaining things are 0. Plus, this is a B. B is nothing that you take here. This is a 1. To order this coefficient, take same coefficient here. So 1, and the remaining thing is 0 here. So now for this one, y is equal to cs plus du. D is always equal to 0. So just you have to go from like this fashion. So like this fashion, you have to go here. So now you have to go in the reverse fashion. So like this, you have to go here from here. So same thing, B A. Don't write any positive or negatives. Keep it as it is. So B A S1 S2 plus 0 into u. So therefore, you are going to get the, just by seeing this one, just by seeing the transfer function, we can write the state model equation. So listen carefully. Y of s by y is equal to s plus b by s square plus ps plus 2. So I can write which is 1 by s square plus ps plus 2 into as plus b. I can write like this. So now, if you say clearly, it is a second order equation. So therefore, you are going to have two state variables, x1 dot x2 dot a into x1 x2 plus b into u. Y is equal to cx plus du. T is always equal to 0. So here you have to go from like this. So therefore, now you have to write in the reverse fashion, minus q minus p. This is 1, this is 0. Here you have to go from in this direction. So BA, take as it is BA without any sign change. D is always equal to 0. In one of this coefficient, take downward. The downward is always equal to 1 and remaining above is always equal to 0. So this way, just by using the transfer function, we can write the state model equation. So this is the state equation and this is the output equation. So overall it is called as the state model equation. Now let's go for the another example. Y of s by u of s is equal to as square plus bs plus c by sq plus ps square plus 2s plus r. So we can write in the same fashion, which is 1 by sq plus ps square plus 2s plus r into as square plus bs plus c. So if you see clearly, I can write in this fashion, right? Which is, so same thing, the order of the system is equal to 3. The characteristic equation order is 3. So therefore, it will have 3 state variables, x1 dot x2 dot x3 dot x1 x2 x3. X dot is equal to ax plus bu. And y is equal to cs plus du. T is always equal to 0. I have already told you in this form, always d you are going to get 0. So 0 into u. So now you have to go from in this direction. So r, q, p. Please write in the negative sign. So minus r, minus q, minus p. So this is 1, yes, this is 0. This is 1, yes, this is 0. Again 1, again 0, like that. So all the remaining things are 0. So here 1 means 0, 1, 0, 1, 0. So always you have to fill like this. And I've already told this last row is always equal to this one. What is this value? Take it as it is here. So this row, the last row is always equal to 1. The remaining things are always 0. So again you have to go from here. CBA. So take it as it is. So CBA in this fashion. CBA. So this is the way that you are going to get. So therefore, if you see clearly, we have basically it is a third order system. So matrix A is 3 by 3. Yet it is a second order system. So matrix A is 2 by 2. So these things always you have to keep in your mind. So therefore, like this always you have to keep in your mind. So like this you have to write. So just by seeing the transfer function, we can write the state model equation. like this. So suppose if they given a differential equation, means apply the Laplace transform and try to get in terms of transfer function and then apply this shortcut in order to get the state model equations. So now let's go for the transfer function. So how to obtain the transfer function from the state model? Suppose if you know the state model, then how to write the transfer function? Reverse of the previous one. The previous case, by knowing the transfer function, we have written how to write the state model. But now reverse fashion. This is on the transfer to the state model, how to write the transfer function that we are going to discuss. So transfer function from the state model, which is, so what is state model? Start of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. So what is the transfer function? Transfer function is output is y of s and input is u of s. So y of s by u of s is equal to c into sa minus a whole inverse into b plus d. So this is a formula always you have to keep in your mind. So c into sa minus a whole inverse into b plus d. Shortcut is cap. C A B cap plus D. So here. So C is used, A is used, B is used. The remaining thing is D. Shortcut is a cap plus D. So therefore C into S I minus A whole inverse into B plus D. So this formula always you have to keep in your mind. So transfer function formula is equal to C into S I minus A whole inverse into B plus D. So this formula always you have to keep in your mind. So x of t is equal to A into x of t plus B into u of t. And y of t is equal to c into x of t plus b into u of t. For the state model, the transfer function y of s by u of s is equal to c into sa minus a whole inverse into b plus d. The transfer function is equal to c into sa minus a whole inverse into b plus d. So just by seeing the state model, we can get the transfer function. So now the next concept is the stability for the system model. So how to figure out the stability from the system model? So suppose if they are given the system model equation, then how to figure out the stability that we are going to figure out? Suppose they are given the system model equation, state equation and output equation. So from this, how to say whether the given system is stable or not, how to see this one that we are going to discuss. So what is the transfer function, from the state model, the transfer function, which is y of s by u of s is equal to c into sa minus a whole inverse into b plus d. So A inverse is nothing but adjoint of A by mod A. So therefore, A inverse is equal to, what is the inverse matrix? A inverse is nothing but A inverse is equal to adjoint of A by mod A. So this one I already told you. Therefore now it is going to become C into adjoint of Si minus A by mod of Si minus A into B plus D. So to simplify, what you are going to get? C into adjoint of Si minus A into B plus D into mod of Si minus A by mod of Si minus A, because this is basically an equation. So that is the reason I am writing like this. So this is basically in terms of transfer function. For this transfer function, what is the characteristic equation? That denominator is called the characteristic equation. So this is the characteristic equation, which is mod of Si minus A. So the closed loop poles are nothing but these are the eigenvalues of the matrix A. So this is nothing but eigenvalues of the matrix A. So therefore the closed loop poles are, it is equal to the eigenvalues of the matrix A. So therefore the characteristic equation is equal to mod of Si minus A is equal to 0. So therefore we can say what is the characteristic equation, which is mod of Si minus A is equal to 0. So if we equate this one to 0, then we are going to get the characteristic equation. So the roots of the characteristic equation are called as the closed loop poles. So these closed loop poles are nothing but these are the eigenvalues of the matrix A, because if you want to figure out the eigenvalues of the matrix A, the format is mod of Si minus A is equal to 0. So in order to figure out the eigenvalues of the matrix A means mod of Si minus A is equal to 0. Similarly, if you want to figure out the closed loops of the closed loop poles, which are is equal to the modulus of the determinant of the Si minus A is equal to 0. So therefore we can say the characteristic equation is equal to the determinant of the Si minus A is equal to 0. So if we expand this one, we are going to get the characteristic equation, and the roots of the characteristic equation are called as the basically the closed loop poles. Similarly, the eigenvalues of the matrix A is nothing but mod of the determinant of the Si minus A is equal to 0. So therefore, the closed loop poles are also called as the eigenvalues of the matrix A. So now, by seeing the characteristic equation roots, we can tell whether a given system is stable or not. If all the roots are going to lie in the list of S plane, then we can say the system is said to be stable. Otherwise, we say it is said to be unstable. So this one I have already told you. If all the poles are going to lie in the list of S plane, irrespective of whether they are repeating or non-repeating, always the system is said to be stable. Suppose if the closed loop poles, if they are non-repeating and if they are lying on imaginary axis, then we can the system is said to be marginally stable. But if you see repeating roots on the imaginary axis, then we guess the system is said to be unstable. If at least any one of the closed loop poles, if it is going to lie in the axis of S-plane, then we can say the system is said to be unstable. So this point I have already told you so many number of times. So just from the system model, we can say the characteristic equation is equal to the determinant of Sm and Sa. So if we equate this one to 0, we are going to get the roots that are closed loop poles which are equal to the eigenvalues of the matrix A. So by comparing the determinant of Sm and Sa is equal to 0 and the S square plus 2 zeta omega ns plus omega n square is equal to 0, we can get the value of the zeta and omega n. So basically, suppose if the system is a second order system, the characteristic equation is the determinant of Sm and Sa is equal to 0. And if you are going to compare the standard second order characteristic equation, which is S square plus 2 zeta omega ns plus omega n square is equal to 0, by comparing these two things, we can say what are the values of zeta and omega n. So therefore, we can say just by seeing the state model, we can say the characteristic equation is the determinant of Sm and Sa is equal to 0. So if we equate this one to 0, we are going to get the closed loop poles which are basically the eigenvalues of the matrix A. Suppose if the order of the system is equal to 2, then the characteristic equation is the determinant of Sm and Sa is equal to 0. So if you are going to compare with the standard second order characteristic equation, which is S square plus 2 zeta omega ns plus omega n square is equal to 0. By comparing these two things, we can get the value of zeta as well as omega. There's another concept, which is the concept of the controllability as well as the observability. So basically, we are going to discuss the concept of the controllability as well as the observability. So what's the meaning of controllability? Controllability is it means to control the state variables, whereas observability means to measure the state variables. So this point always you have to keep in your mind. So controllability, basically, it means to control the state variables, whereas the observability means to measure the state variables. So this concept always you have to keep in your mind. So therefore, we can say controllability always, it means that we have to control the state variables, and observability is basically, it means that to measure the state variables. Suppose if any one of the state variables is not controlled, then we can say it is an uncontrolled system. Suppose if any one of the state variable that we can't measure, then we say it is a unobservable system. So listen carefully. If all the state variables of a system are controlled, then it is called as a controllable system. If any one of the state variable is not controlled, then it is called as the uncontrollability. Suppose if all the state variables are measured, then we say it is said to be observability. If any one of the state variable, if we can't measure, then it is called as the unobservability. So this point always you have to keep it in mind. So controllability basically it means to control the state variables, and observability means to measure the state variables. If all the state variables are controlled, then it is called as a controllable system. If any one of the state variable is not controlled, then it is called as an uncontrollable system. If all the state variables are measured, then it is called as the observability system. If any one of the state variable is not measured, then it is called as the unobservable system. So for a given state model, how to say whether a given system is controllable, how to say it is a uncontrollable, if it is a controllable or uncontrollable or observable, how to measure. So how to figure out with the help of the Kalman's test. So if you know the state model of a system, then by using this Kalman test, we can say whether a system is controllable or uncontrollable, or whether it is observable or unobservable, we can easily say. So what is the controllability matrix, which is equal to B, AB, A square B up to A to the power of n minus 1 B. And the order of this matrix is always equal to n by n, where n is the order of the matrix A also. So for A matrix, the order is n by n. So n by n is the order of the matrix A. So therefore, similarly, the controllable matrix order is also equal to n by n. So this point always you have to keep in your mind. So therefore, we can say whatever the order of the matrix A is same as the order of the controllability matrix also. So this is basically column elements up to A to the power of n minus 1 into B. So this is the n cross n matrix. Similarly, observability matrix is also. So replace B by C transpose and replace A by A transpose. We are going to get C transpose, A transpose, C transpose, A transpose whole square, C transpose, A transpose whole to the power of n minus 1 into C transpose. So it is also n by n matrix. It is also n by n matrix. So replace B by A transpose and replace A by A transpose. Replace B by C transpose and replace A by A transpose. then we are going to get the observability matrix. It is also n by n matrix. So see, in the ABCD, C is going to come earlier than O. So therefore, this is a controllable, this is observable. So controllability matrix is equal to B, AB, A square B, up to n to the power of n minus 1 into B. And this order of this matrix is equal to n by n. And the observability matrix is replace B by C transpose and A by A transpose. We are going to get C transpose, A transpose, C transpose, A transpose whole square to B transpose, and goes on up to A transpose 1 to the power of n minus 1 into C transpose. So this is also n by n matrix. So the matrix A order is n by n. Similarly, the matrix QC and the matrix QO are also same order, which is n by n. Suppose if the determinant of the controllable matrix is not equal to 0, then only we can say it is a controllable matrix. Otherwise, it is said to be uncontrollable. If the determinant of the observability matrix is not equal to 0, then only we can say it is observable. Otherwise, it is unobservable. So always you have to remember, if it is not equal to 0 means controllable, otherwise uncontrollable. If it is not equal to 0 means it is observable, otherwise it is not observable. Where n is the order of the matrix here, I have already told you. So therefore we can say, if the determinant of the controllability matrix, if it is not equal to 0, then only we can say it is a controllable. If it is equal to 0 means uncontrollable. Similarly, the determinant of the observability matrix, if it is not equal to 0 means then only we say it is an observable matrix. Otherwise, we say it is a unobservable matrix. So finally, I can say controllability basically it means we have to control the state variables. Observability basically means to measure the state variables. If all the state variables are controlled, then only we can say the system is said to be controllable system. If any one of the state variables is not controlled, then we say it is an uncontrollable system. Similarly, if all the state variables are measured, then only we say it is a observable system. If any one of the state variable is not measured, then we say it is said to be unobservable system. So for a given state model, how to say whether it is a controllable or uncontrollable, observable or unobservable? Just by applying the Kalman's test, we can say this one. So controllability matrix is B, AB, A square B, up to n to the power of n minus 1 into B. Whereas the order of the matrix A is n by n. Similarly, the order of the controllable matrix is also equal to n by n. And the observability matrix is replace B by C transpose and replace A by A transpose. We are going to get C transpose, A transpose, C transpose, A transpose whole square into C transpose, and goes on up to A transpose 1 to the power of n minus 1 into C transpose. And the order of the observability matrix is also equal to n by n. So whatever the order of matrix is, same is the order of both the QC as well as the QO. If the determinant of the controllable matrix which is not equal to 0, then we can say it is a controllable. If it is equal to 0 means it is uncontrollable. If the determinant of the observability matrix if it is not equal to 0 means it is observable. Otherwise it is unobservable. Where n is called as the order of the matrix A. So this point always you have to keep in your mind. Now let's go for the another concept, which is the solution of the state equation. So now we are going to figure out what is the solution of the state equations. Now we are going to figure out. So basically the state model equations which is x dot of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. So we are going to figure out the solution of the state equation, which is the x dot of t is equal to a into x of t plus b into u of t. This is called the state equation. So now we are going to study zero input response or free response. This input is not applied, but still you are going to get some output that is called as a free response. So even though input is equal to 0, still you are going to get some output because of the state variables. That is called as the free response. So even though input is equal to 0, we are going to get the output because of state variables. That is called as the zero input response or free response. Yes, input u of t is equal to 0 means input is basically u of t. So u of t I am going to make it as 0, and then I will see what is the output that I am going to get. So if you apply u of t is equal to 0, then you are going to get x dot of t is equal to a into x of t. So if I am going to apply the Laplace transform on both sides, then I am going to get s into x of s minus x of 0 is equal to a into x of s. So if you take this x of s to the left side and this x naught to the right side, we are going to get x of s into si minus a is equal to x naught of 0. So if you apply inverse on both sides, we are going to get x of s is equal to x naught into si minus a whole inverse. So basically we can say x naught is scalar quantity. We can write either here or either we can write front and then which is same. So therefore we can say x of s is equal to x naught into si minus a whole inverse. Then what is x of t? Apply the Laplace inverse. We are going to get x of t is equal to Laplace inverse of SA minus A whole inverse into x naught. So x naught is a constant, we can take it outside the Laplace inverse. So therefore, we can say we are going to get like this. So if you are going to apply Laplace inverse, we are going to get like this, which is Laplace inverse of SA minus A whole inverse into x naught. But x naught is a constant, we can take it outside this one. So therefore, Laplace inverse of SA minus A whole inverse into x of 0. So this is the response that we are going to get x of t for the input is equal to 0. So we can write in other fashion also. We can solve this one in the other format also. S dot of t is equal to a into x of t. So this is one way. Other way also we can solve. S dot of t is equal to a into x of t. So if I take this one to the LHS, we are going to get x dot of t minus a into x of t is equal to 0. Then s dot of t minus a into x of t is equal to 0. Then what is the x of t? So you can see basically this is the, so if you apply the derivative, so basically dy by dt I am going to assume it is equal to d. So d minus a is equal to 0. So d is equal to a. Then what is the response? X of t is equal to some constant into e to the power of a into t. So with the help of differentiation concept, we are going to get the response. X of t is equal to k into e to the power of at. So like this we are going to get. So this is basically the Laplace transform. This is basically with the help of the differentiation concept. So x of t is equal to k into e to the power of at. You can write k anywhere you are going to write here. So by comparing these two equations, we can say simply k is nothing but x of 0 and e to the power of at is nothing but Laplace inverse of SA minus A whole inverse. So by comparing these two things, we can say k is equal to x of 0 and e to the power of at is nothing but Laplace inverse of SA minus A whole inverse. So this we can see clearly here. So by comparing these two, so this is the solution we are going to get by Laplace domain, and this is the solution we are going to get by differential concept. So k is equal to x of 0 and e to the power of at is equal to Laplace inverse of SA minus A whole inverse. So now, so listen carefully. So we got x of t is equal to e to the power of at into k. So now in place of t, I want to substitute 0. Then what we are going to get? X of t as a t tends to 0 is equal to e to the power of a. In place of t, substitute 0, e to the power of a into 0 into k. So e to the power of a is nothing but 1. So 1 into k is equal to k, but k is equal to x of 0. So therefore we are going to get x of 0. So therefore we can say in this x of t, if you are going to substitute t is equal to 0, then what you are going to get? This value is going to become 1 and this value you are going to k. K is nothing but x of 0. So therefore x of t at t is equal to 0 is equal to x of 0 you are going to get. So these things you can see clearly here. So this is the free response. So free response. So now what is the forced response? So forced response, what we are going to get? So forced response means input is not equal to 0. So input is not equal to 0. So therefore we can say x dot of t is equal to a into x of t plus b into u of t. So I am going to apply the Laplace transform of both sides. Then we are going to get s into x of s minus x dot of 0 is equal to a into x of s plus b into u of s. So if you take the x of s here and if you take x naught here, we are going to get s a minus a into x of s is equal to x naught plus b into u of s. So if you apply the Laplace inverse, this s a minus a inverse on both sides, then we are going to get x of s is equal to s a minus a inverse into x of 0 plus s a minus a inverse into b into u of s. So this is what that we are going to get. So basically now this is in terms of s domain. I want to get in terms of time domain. So replace s by, so after the Laplace inverse we are going to get x of t is equal to Laplace inverse of s a minus a whole inverse into x naught of 0 plus Laplace inverse of s a minus a whole inverse b into u of s. As x naught is a constant, we can take it outside the Laplace inverse. So therefore we can say x of t is equal to Laplace inverse of s a minus a whole inverse into x of 0 plus Laplace inverse of s a minus a whole inverse into b into u of s. So this is the thing that we are going to get. So you know what is basically output equation? Y of t is equal to c into x of t plus d into u of t. So in the case of free response, u of t is equal to 0. And you know the value of x of t, they substitute and get the value of output response. Suppose for the forced response, you got the value of x of t, they substitute here, and if you simplify this equation, we are going to get the y of t. So therefore, we are going to get the free response as well as the forced response also. We are going to get with the help of x of t. So if you know x of t, you substitute in this output equation and you are going to get the corresponding output. The response or the forced response. So therefore we can say for a zero input response, x of t is equal to Laplace inverse of x of 0 into Laplace inverse of Si minus a whole inverse. Whereas for forced response, x of t is equal to Laplace inverse of Si minus a whole inverse into x of 0 plus Laplace inverse of Si minus a whole inverse into b into u of s. So these things always you have to keep in your mind. So finally, I am going to write here, listen carefully, the value of x of t. So the value of x of t for free response, which is equal to x of 0 into Laplace inverse of Si minus a whole inverse. So this will always you have to keep in your mind. For forced response, x of t is equal to x of 0 into Laplace inverse of Si minus a whole inverse plus Laplace inverse of Si minus a whole inverse into b into u of s. So these formulas always you have to keep in mind. So this is the extra factor that we have to add for the forced response. So this is the extra factor that we have to add for the forced response. So therefore x of t is equal to x of 0 into Laplace inverse of Si minus a whole inverse for free response, and for forced response, which is x of t is equal to x of 0 into Laplace inverse of Si minus a whole inverse plus Laplace inverse of Si minus a whole inverse into b into u of s. So these things always you have to keep in your mind. Now we are going to discuss the properties of the transition matrix, state transition matrix. So now we are going to discuss some properties of the state transition matrix. So the state transition matrix is nothing but phi of t. So phi of t is called as the state transition matrix, which is equal to e to the power of at. So we already told you what is the state transition matrix we are going to assume, which is phi of t. So phi of t is equal to e to the power of at. So e to the power of at, you know, which is equal to, just now we have discussed, Laplace inverse of Si minus a whole inverse. So this one I already told you. So now we can see Laplace inverse of Si minus a whole inverse. Just now we have seen this one. So what is a state transition matrix? Phi of t is equal to e to the power of at into at is equal to Laplace inverse of Si minus a whole inverse. So this is the concept always you have to keep in your mind. So this is the state transition matrix, which is phi of t is equal to e to the power of at is equal to Laplace inverse of Si minus a whole inverse. So suppose at t, if I am going to substitute t is equal to 0, then what we are going to get? Phi of t at t is equal to 0, then here we are going to get 1. 1 is nothing but identity matrix. So here we are going to get basically identity matrix that we are going to get. So therefore we are going to get I. So state matrix at t is equal to 0, we are going to get the identity matrix that we are going to get here. So now phi of t is equal to e to the power of at, then what is phi dash of t? Is derivative. So derivative is nothing but a into e to the power of at with respect to t. So phi dash of t is equal to a into e to the power of at. Then I will substitute here t is equal to 0. Then we are going to get a matrix. So phi dash of t at t is equal to 0, we are going to get this value is equal to a, because this value is equal to 1, and a is equal to a you are going to get. Then phi of t1 plus t2. Phi of t1 plus t2 is nothing but in place of t substitute. In place of t substitute t1 plus t2. So e to the power of a into t1 plus t2. So you can write e to the power of m plus n is equal to e to the power of m into e to the power of n. So e to the power of a t1 into e to the power of a t2. So e to the power of a t1 is phi of t1 and e to the power of a t2 is phi of t2. So therefore we can say phi of t1 plus t2 is equal to phi of t1 into phi of t2. We can see clearly from this picture. And phi of t whole inverse. Phi of t whole inverse is nothing but phi of t whole inverse is nothing but phi of t, you know, e to the power of a whole inverse is nothing but like this. Then what we can say, e to the power of a into minus t also we can write is equal to phi of minus t. So these are the properties always you have to keep in mind. So finally, I can write all the properties here. Listen carefully. So finally, I am going to write all the properties. So phi of t is equal to state transition matrix is equal to e to the power of at is equal to Laplace inverse of Si minus a whole inverse. Similarly, phi of t at t is equal to 0. T is equal to 0, you are going to get identity matrix. And phi dash of t at t is equal to 0, you are going to get matrix as A. Similarly, the other is phi of t1 plus t2 is always equal to phi of t1 into phi of t2. Similarly, phi of t over the whole inverse is nothing but phi of minus t. So this is t by minus t, we are going to get this one. So this is something always you have to keep in your mind. So basically, whatever this Laplace inverse, finally we are going to get in terms of time domain only. So whatever this Laplace inverse, finally we are going to get. So if the Laplace inverse of Si minus I whole inverse, we are going to, in terms of time domain only, we are going to get. So if we want phi of t whole inverse means, just replace t by minus t, then we are going to get this value. So phi of t whole inverse. So this is something always you have to keep in your mind. So this is the matrix you are going to get in terms of time domain you are going to get. So these things always you have to keep in your mind. So finally I can say phi of t is from straight transition matrix. Its value is equal to power of At is equal to Laplace inverse of Si minus I whole inverse. And phi of t at t is equal to 0, we are going to get empty matrix. And phi dash of t at t is equal to 0, we are going to get matrix A. And phi of t1 plus t2 is equal to phi of t1 to phi of t2. And phi of t whole inverse is equal to phi of minus 2. So whatever this phi of t is, basically this is all in terms of time domain only we are going to get. So these things always you have to keep in your mind. So these are some of the formulas regarding the control system. So these are the actual formulas of control systems that we have discussed in a very detailed manner. Now we are going to discuss some more important points regarding the control systems in a very detailed manner. So listen carefully. The sensitivity of alpha with respect to beta is equal to the sensitivity of alpha with respect to beta. I have already told you. So if your alpha means in this function you have to write here. So this one I have already told you. And beta means here like this you have to write here. So this one I have already told you. So therefore we can say the sensitivity of alpha with respect to beta is equal to beta by alpha into d alpha by d beta. So this is a shortcut to remember. So I have already told you what is the shortcut to remember also, as I have already told you. So therefore we can say that the sensitivity of alpha with respect to beta is equal to beta by alpha into d alpha by d beta. So here b means here also beta, here also beta. Here alpha means here alpha, here alpha. So this is d alpha by d beta. So you can also write in another form of this d alpha by d beta by beta. So if we rewrite this one, we are going to get beta by alpha into d alpha by d beta. So like this also you can write, or you can say the percentage change in the alpha by the percentage change in the beta. So these are the different ways that we are going to write here. So always remember the sensitivity of alpha with respect to beta is equal to d alpha by d beta by beta. So if you raise this one, we are going to get beta by alpha into d alpha by d beta. It is also called as a percentage change in the alpha by the percentage change in the beta. So this point always you have to keep in your mind. So therefore we can say the sensitivity of alpha with respect to beta is equal to d alpha by d beta by beta. If you rewrite this one, we are going to get beta by alpha into d alpha by d beta. It is also equal to the percentage change in the alpha by the percentage change in the beta. So this point always you have to keep in your mind. So finally I can say the sensitivity of alpha with respect to beta is equal to d alpha by d beta by beta. So you can write beta by alpha into d alpha by d beta. So here is alpha means here alpha, here beta means here beta, here beta. It is also equal to percentage change in the alpha by the percentage change in the beta. Now the next point is a closed loop control system is more sensitive to variations in feedback elements h of s than the forward path elements g of s. So this one I have already told you. In a closed loop control system, it is more sensitive to the variations in the feedback element h of s than the forward path elements g of s. So this one I have already told you, which is the sensitivity of the m of s with respect to h of s. This is the magnitude value as I have already told you, which is equal to g of s into h of s by 1 plus g of s h of s. So this one I have already told you. Whereas the sensitivity of m of s with respect to g of s is equal to 1 by 1 plus g of s h of s. So by this we can say that whatever the sensitivity of the m of s with respect to h of s is always higher when compared to the sensitivity of m of s with respect to g of s. So this one I have already told you so many more times. So therefore we can say that in the case of closed loop control system, it is basically more sensitive to the variations in the feedback element h of s than the forward path elements g of s. So suppose if there is a small amount of variation in the feedback element, then the output is going to change more when compared to the variations in the g of s. So therefore we can say a closed loop control system is more sensitive to variations in the feedback element h of s than the variations in the fault path element at G of S. So therefore we can say a closed loop control system is more sensitive to variations in the feedback element H of S than the variations in the fault path element G of S. So therefore we can say the sensitivity of M of S with respect to H of S is equal to the neighborhood value is equal to G of H of S by 1 plus G of S H of S. Whereas the sensitivity of M of S with respect to G of S, the neighborhood value is equal to 1 by 1 plus G of S H of S. So these things I already told you so many number of times. Then the derivative of the parabolic response is equal to ramp response, and the derivative of the ramp response is equal to step response. The derivative of the step response is equal to impulse response, and the derivative of the Laplace transform of impulse response is equal to transfer function. So this one I have already told you so many number of times. So derivative of the parabolic response, you are going to get the ramp response, and derivative of the ramp response, you are going to get the step response, and derivative of the step response, you are going to get the impulse response. Similarly, the Laplace transform of the impulse response is nothing but this called as the transfer function. So this point I have already told you so many number of times. So therefore we can say the derivative of the parabolic response is equal to ramp response, and derivative of the ramp response is equal to step response, and derivative of the step response is equal to impulse response, and the Laplace transform of the impulse response is equal to transfer function. So this point I have already told you so many number of times. And the reverse is also true, which is the integration of the impulse response is the step response, and the integration of the step response is the ramp response, and the integration of the ramp response is the parabolic response. So like this also we can do this one. So finally I can say the derivative of the parabolic response is ramp response, the derivative of the ramp response is step response, the derivative of the step response is impulse response, and the Laplace transform of the impulse response is equal to the transfer function of the system. The vice versa is also true, which is the integration of the ramp response is parabolic response, and the integration of the step response is ramp response, and the integration of the impulse response is step response. So these things always you have to keep in mind. So now the next thing is, from closed loop transfer function, we can figure out the open loop transfer function by this way, which is, suppose if you know the closed loop transfer function, so how to get the open loop transfer function means, in the question they are given the closed loop transfer function. Closed loop transfer function is equal to numerator by denominator they have given. So now we have to get the open loop transfer function, which is numerator by denominator minus numerator. So this is a condition. The condition is always H of S is always equal to 1. So under this condition only we are going to get this one. Otherwise this shortcut is valid only for whenever the H of S is equal to 1. Otherwise this the shortcut is not valid. So therefore we can say that suppose if the given the closed loop transfer function is ratio of the numerator by denominator, then the open loop transfer function is equal to numerator by denominator minus numerator. So this one, the shortcut is going to valid only when the H of S is equal to 1. So what is the open loop transfer function? G of S into H of S, and H of S is equal to 1. So therefore we are going to get the open loop transfer function is equal to G of S. So from open loop transfer function, we can figure out the closed loop transfer function. Suppose if they are given the open loop transfer function, which is equal to open loop transfer function, if they are given numerator by denominator, then how to figure out the closed loop transfer function, which is equal to numerator by denominator plus numerator. So this one always you have to keep in the mind. So basically, see, suppose if we are given the closed loop, if we want the open loop means we have to remove the feedback, plus remove means subtraction. Suppose if they are given the open loop transfer function, so we need a closed loop transfer function means basically we need feedback. So feedback means we have to keep it here. So we have to keep means keep positive. So keep positive. So remove means negative, keep means positive. So have to remember. So remove means we have to keep negative, and we have to keep means it is a positive. So have to remember. So if they given the closed loop transfer function, which is the numerator by denominator, then the open loop transfer function is equal to numerator by denominator minus numerator. Suppose if they are given the open loop transfer function as numerator by denominator, the closed loop transfer function is equal to numerator by the denominator plus numerator. So basically, your open loop transfer function is here. Basically, removing the feedback from closed loop transfer function. Remove means keep negative. Here, from open loop, if you are going to get the closed loop, means you have to keep the feedback. So if you are going to keep the feedback, is keep positive. Shortcut to remember. So removing the feedback means keep negative. Closing the feedback means keep positive. So this is a shortcut to remember. So these two formulas are valid only when H of S is equal to 1. Otherwise, these are not valid. So these formulas are valid only when the h of s is equal to 1. So this point always you have to keep in your mind. So these two formulas are valid only when the h of s is equal to 1. Otherwise, these two formulas are not valid. So finally, I can say, suppose if they are given the closed loop transfer function, which is denoted by denominator, then if you want the open loop transfer function is, we have to remove the feedback from the closed loop transfer function is, remove means keep negative, so therefore open loop transfer function is equal to numerator by denominator minus numerator. Suppose if they given the open loop transfer function which is equal to numerator by denominator, so if you want the closed loop transfer function, so from open loop you have to give a feedback in order to get the closed loop. So keeping means give the positive sign in denominator, so therefore we can say denominator by numerator plus denominator. So these two shortcuts are going to valid only when the h of s is equal to 1. So these are valid only for h of s is equal to 1. Otherwise, these are not valid. Open loop transfer function is 3 of s into h of s. So these things always you have to keep in your mind. And the Laplace transform of f of t minus a into u of t minus a is equal to e to the power of minus as into f of s. So this one always you have to keep in your mind. So therefore, we can say, suppose for f of t, if f of t, the Laplace transform is f of s. So for f of t, if the Laplace transform is f of s, then f of t minus a into u of t minus a has the Laplace transform, which is e to the power of minus as into f of s. So this is always this formula is very much important. So therefore we can say, for f of t, if the Laplace transform is f of s, then f of t minus a into u of t minus a has the Laplace transform e to the power of minus as into f of s. So this one always you have to keep in your mind. So therefore we can say, if f of t has the Laplace transform f of s, then f of t minus a into u of t minus a has the Laplace transform e to the power of minus as into f of s. So this formula always you have to keep in your mind. So therefore we can say, for f of t, if the Laplace transform is f of s, then f of t minus a into u of t minus a has the Laplace transform e to the power of minus as into f of s. So these things always you have to keep in your mind. Next point is, for initial relaxed system, for any input, the response of t at t is equal to 0 is equal to 0. So what is the meaning of initial relaxed system? Initial relaxed system means, before this means at t less than 0, the input is equal to 0, so output is also equal to 0. So whenever the input we are going to give at t is equal to 0, so the response we are going to get at t is equal to 0 is always equal to 0. So therefore, for initial relaxed system, for any input, the response always c of t at t is equal to 0 is always equal to 0. Means the response is going to start from 0 always. So for any relaxed system, always the response c of t at t is equal to 0 is always equal to 0. So therefore we can say, for initial relaxed system, for any input, the response c of t at t is equal to 0 is always equal to 0. So this point always you have to keep in your mind. Therefore, in simple words, I can say like this. So basically, suppose for an initial relaxed system, suppose if you are going to give any arbitrary input, as system is a relaxed system, so definitely the response of t at t is always equal to 0 is always equal to 0, means it is going to start from 0 always without any non-zero value. So it is always going to start from the 0. That is the basic meaning of the initial relaxed system. So for initial relaxed system, we can say for any input, the response of t at t is equal to 0 is always equal to 0. So finally, I can say for any relaxed system, no matter whatever the input, the output is always going to start from 0 itself. So therefore, we can say the c of t at t is equal to 0 is equal to 0. The next point is, the system DC gain corresponds to the steady state value of the unit step response. The system DC gain corresponds to the steady state value of the unit step response. So basically, what is the meaning of this one? Is basically, suppose if you take a transfer function, so suppose for a system, if we are going to give a step input, then we are going to get the unit step response. So for this unit step response, I want to find what is the steady state value. So for this unit step response, I want to know what is the steady state value. The steady state value itself is the DC gain in the transfer function. So whatever the DC gain in the transfer function, that is called as the steady state value of the unit step response. So listen carefully. Suppose for a given system there is a transfer function. So transfer function is basically it will have some constant k. So k is called as a DC gain. So DC gain we can say some k dash of k. So now I want to know what is the steady state value of the unit step response. For the system, if we are going to give the unit step, then we are going to get the unit step response. And I want to know what is the steady state value I'm going to figure out. So steady state value is nothing but it is basically the DC gain corresponds to the steady state value of the unit step response. So whatever the DC gain of the transfer function, that is going to call as the steady state value of the unit step response. So now you can see clearly, see C of t is nothing but it is a unit step response. So limit tends to infinity, C of t is equal to, by applying the final value theta, we can say limit s tends to 0 s into C of s. So this is called as the steady state value or the final value or the DC gain, which is basically equal to K dash. So C of t is called unit step response. So limit tends to infinity, C of t is equal to limit s tends to 0 s into C of s. It is called as the steady state value or the final value or the DC gain, which is equal to K dash. Or simply you can say C of s by R of x is equal to transfer function. So you know the R of s value is equal to 1 by s. Let's substitute in the value of this one, and if we simplify, we are going to get the steady state value of this response that we are going to get, which is nothing but DC gain. So this is the meaning of this one. So the next question is, the next concept is, linear capacitor is basically used for improving the transient state characteristics, whereas the lag capacitor is basically used for the elimination of the steady state error, whereas the lag gate capacitor used for the elimination of the steady state error as well as the increasing the speed of response means transient characteristics. I've already told you the linear capacitor is basically used for improving the transient state characteristics means it is going to decrease the rise time, means it is going to increase speed of the response. So as the rise time decreases, bandwidth will increase, and also it is going to increase the gain crossover frequency. Whereas in the case of lag capacitor, it is basically used to improve the steady state response, means it is going to eliminate the steady state error, means the steady error will be decreasing with the help of lag capacitor, and it is going to decrease the gain crossover frequency. Whereas the lagged capacitor is basically used to improve both the transient response as well as the steady state response. Means it is going to increase the speed of the response as well as it is going to decrease the steady state error. So these things always you have to keep in mind. So finally, I can say that linear capacitor is basically it is used for improving the transient state characteristics, means it is going to increase the speed of the response, means the rise time is going to get decreased, and it's also going to increase the gain crossover frequency. Whereas the lag capacitor is basically it is used to improve the steady state characteristics, means it's going to decrease the steady state error. And the lag capacitor is basically it is used for it is going to improve both the transient state characteristics as well as the steady state characteristics. So we can say it is going to increase the speed of the response as well as it is going to decrease the steady state error. So I already told you one important thing: the lead has more volts, the transit has more volts, lag has less volts, and the steady has less volts. So match two things of more volts and match two things of less volts. So lead capacitor is basically it is used to improve the transient response, whereas the lag capacitor is basically it is used to improve the steady response. The next thing is d'Alembert law is nearly equal to Kirchhoff's law, and we can say both are the analogous. So d'Alembert law is applied in the mechanical circuits, whereas the Kirchhoff's law is used in the electrical circuits. So therefore we can say these are analogous equations. So Kirchhoff's law is basically applied in the electrical circuits. Similarly, d'Alembert law is applied in the mechanical circuits. So we can say these both are the analogous equations. So the Kirchhoff's law is going to apply in the electrical circuits, and the d'Alembert law is applied in the mechanical circuits, and both have the same amount of behavior. So these two are called as the we can say analogous equations. So we can say Kirchhoff's law is basically used in electrical circuits, whereas the d'Alembert law is used in the mechanical circuits. So these both the phenomena are the we can say the both type of these equations, the nature is same. So therefore we can say these two are the analogous equations. The next point is, in a signal flow graph, output can be defined across any node by extending it with the unit gain. So in the case of signal flow graph, output can be defined across any node just by extending that node with the unit gain. So this one I already told you. In the case of signal flow graph, output can be defined across any node just by extending that particular node by the unit gain. So always remember, in the case of signal flow graph, output can be defined across any node just by extending that particular node by unit gain. So listen carefully. In the case of signal flow graph, output can be defined across any node just by extending that particular node by the unit gain. So in the case of signal flow graph, output can be defined across any node just by extending that particular node with the unit gain. The next one is self loops on the input node are not a loops, whereas the self loops on the output node is a valid loop. So this part always you have to keep in mind. So whatever the self loops which are going to present on the input node, these are not the loops, these are not the valid loops, whereas the self loops on the output node is a valid loop. So this is the important concept always you have to keep in your mind. So whatever the self loop on the input node is not a loop, it is not a valid loop, whereas the self loop on the output node is considered as it is a valid loop. So this is an important point always you have to keep in your mind. So therefore we can say whatever the self loop on the input node is not a valid loop, whereas the self loop on the output node is a valid loop. So this point always you have to keep in your mind. So therefore we can say the self loop on the input node is considered as a valid is not a valid loop, whereas the self loop on the output node is considered as a valid loop. So therefore we can say finally the self loop on the input node it is not a valid loop, whereas the self loop on the output node is a valid loop. So finally I can say whatever the self loop on the input node is not a valid loop, whereas the self loop on the output node is considered as the valid loop. The next one is the taking the summing point as a node and also the takeoff point as a node in order to convert the block diagram to signal flow graph. So this one I already told you, taking the summing point as a node and also taking the off point as the node in order to convert the block diagram into signal flow graph. So what are the things that are required in order to convert the block diagram into a signal flow graph is we have to assume the sum point as a node as also the takeoff point is also node. So if we consider these two things, then it is basically we are going to convert the block diagram to the signal flow graph. So therefore we can say we have to assume the summing point as a node as well as the takeoff point as a node. Then we are going to convert the block diagram into the signal flow graph. So therefore we can say we are going to assume the summing point as a node as well as the takeoff point as a node. So by this we are going to convert the block diagram into a signal flow graph. So take the summing point as a node and also the takeoff point as a node in order to convert the block diagram to the signal flow graph. So in simple words I can say like this. Basically if I am going to see the basic way, the standard way to convert the block diagram to the signal flow graph is we have to assume the summing point as a node as well as the takeoff point as a node. Then we are going to convert the block diagram to the signal flow graph. So finally I can say we are going to assume the summing point as a node as well as the takeoff point as a node. So therefore by this way we are going to convert the block diagram to the signal flow graph. The next one is since most of the control systems operate with low power ratings and in low frequency range, so they are said to be analogous to low pass filters. So listen carefully. Since most of the control systems operate with the low power ratings and also in the low frequency range, so they are said to be analogous to the low pass filters. So we can say since most of the control systems they have the very low power ratings and also they are going to operate only in the low frequency range, so therefore we can say these are analogous to the low pass filters. So we can say most of the control systems basically they are going to operate with the low power ratings and also they are basically operating in the low frequency range. So based on this we can say they are basically analogous to the low pass filters. So simply I can say since most of the control systems they are going to operate with the low power ratings and also they are going to operate in the low frequency range. So because of this we say these are analogous to the low pass filters. So when I can say since most of the control systems they are going to operate with the low power ratings and also in the low frequency range, so therefore we can say they are basically said to be analogous to the low pass filters. The next one is whenever a pole is added to transfer function, then its stability decreases and the root locus is going to shift to the right hand side. Whereas whenever a 0 is added to the transfer function, then its stability increases and the root locus is going to shift to the left hand side. So this point I have already told you. Suppose whenever you are going to add a pole to the open loop transfer function g of s h of s, then the stability is going to get decreased because the root locus is going to shift to the right hand side. But whenever you are going to add a 0 to the open loop transfer function g of s of s, so the stability is going to get increased, means the root locus is going to shift to the left hand side. So this point always you have to keep in your mind. So therefore we can say whenever you are going to add a pole to the open loop transfer function, then the stability is going to get decreases because the root locus is going to shift to the right hand side. But if you are going to add a 0 to the open loop transfer function, then the stability is going to get increases and the root locus is going to shift to the left hand side. So finally I can say whenever you are going to add a pole to a open loop transfer function g of h of s, then the stability is going to get decreases because the root locus is going to shift to the right hand side. But if you are going to add a 0 to the open loop transfer function g of h of s, then the stability is going to get increases and the root locus is going to shift to the left hand side. So now the next point is, so listen carefully here. Suppose there is an open loop transfer function like this, which is g of s into h of s is equal to k into s plus b by s into s plus a. So this is the open loop transfer function k into s plus b by s into s plus a. So now I am going to this time draw the pole 0 plot on the S plane. So 0 is minus b and the poles are 0 and minus a. So you can see the poles are 0, minus a and the 0 is minus b for this open loop transfer function. So based on this I want to draw the root locus diagram for this open loop transfer function I want to draw. Then what we are going to get, so if I am going to stand here and if I am going to see to my right side, the summation of the real poles, real open loop poles and real open loop zeros is equal to 1. So it's the odd number. So yes, this part is present in the two papers. But if I start here and if I sit to my right side, we can say the summation of the real open loop poles and real open loop zeros, the summation is equal to 2, is an even number. So which is not in the two papers. Similarly, if I stand here, then if I sit to my right side, then I can say the summation of the real open loop poles and the real open loop zeros, the summation is odd. So this is also in the two papers. So this part is there, this part is there. But here, if I stand here and if I see to my right side, the summation of the real open loop poles and real open loop zeros, which is basically 0, is an even number. So this is not in the two papers. So this part is there, this part is there. So these two root locus branches, they are going to come together and they are going to intersect and they are going to go like this finally. Again, where they are going to break away, where they are going to break in. Again, one root locus branch will go to 0 and the other root locus branch will go to infinity. So this is the, we can say, the root locus diagram that we are going to get. So it's basically, this root locus diagram is basically a circle we are going to get. So this is basically circle part we are going to get with the center minus b comma 0 and the radius is equal to root over b into b minus a. So this one always you have to keep in mind. So what is the center of this? The center of the circle, the center of this. So this root locus is basically, it is in the form of a circle, the center minus b comma 0 and the radius is nothing but which is equal to root over b into b minus a. So this one always you have to keep in your mind. Then what is the breakaway points? So this is the breakaway point. So this is what is the breakaway point, which is, you can say, center. So this is the basically, so this is also breaking point and this is also break. So these two are called the breakaway points, simply we can say. So therefore, what is this one? We can say center plus or minus radius. Suppose this is the center plus minus b. So minus b. So this is a minus b, right? Center means this is a minus b. So minus b minus radius. Then you are going to get this point. Minus b plus r. Then you are going to get this point. So this is what I am trying to tell you. So minus b minus r means we are going to get this point. Minus b plus r means we are going to get this point. So these are the breakaway points for this one. So always remember, if the open loop transfer function is equal to k into s plus b by s into s plus a, then we are going to get a root locus in a circle shape with the center minus b comma 0 and the radius of this root locus is root locus is equal to root over b into b minus a. Whereas the breakaway points are center with the radius. Center plus or minus radius means minus b minus r minus b plus r. So like this we are going to get. So minus b minus r means we are going to get this point. minus b plus r means we are going to get this point. So finally I can say if the open loop transfer function in the format g of h of s is equal to k into s plus b by s into s plus a, then if you are going to draw the root locus, we are going to get root locus in a circle shape we are going to get, and this root locus is going to have a center of minus b comma 0, and the radius of this root locus is under root over b into b minus a, and the breakaway points are which is center plus or minus radius means minus b minus r means we are going to get this point, minus b plus r means we are going to get this point. So these are the breakaway points. So now let's go for the another one, which is g of s h of s is equal to k by s into s plus a into s plus b. So this is an open loop transfer function. Then the root locus is going to cut the j omega axis at a particular point, which is equal to s is equal to plus or minus j into under root over ab. So this is a shortcut formula. So if we actually, what is the actual procedure? So just to get the transfer, the calistic equation which is 1 by g of h of s equal to 0, then with the help of RH criteria, try to figure out the k marginal and substitute the k marginal in the algebraic equation and then find the value of s. So there we are going to get the value of s at which the root locus is going to cut the imaginary axis. That is the standard procedure. But it will take a lot of time. So if any transfer function, the overall transfer function in the format of k by s into s plus a into s plus b, so in the direct formula which is the root locus is going to cut the imaginary axis or the j omega axis at the particular point which is equal to s is equal to plus or minus j into under root over ab. So this is a shortcut formula you have to keep in your mind. So therefore we can say the way to the actual standard procedure in order to get the points where the root locus is going to cut the imaginary axis, which is first write the calistic equation 1 plus g of h of is equal to 0, and with the help of RH table try to figure out the k marginal and keep this k marginal in the root in the auxiliary equation and get the value of s. So at these points the root locus is going to cut the imaginary axis. That is the actual procedure. But if you want to make a shortcut for this type of transfer function, open transfer function, which is g of h of is equal to k by s into s plus a into s plus b, and the root locus is going to cut the imaginary axis on the j omega axis at s is equal to plus or minus j into under root over ab. So this formula always should be keep in your mind. So now the next concept is, suppose if you take a S-plane, like this. Suppose I am going to have some 4 roots. So I am going to have some 4 poles for this open loop transfer function g of h of s, and I am going to plot in this manner. So you can see here there is a one pole, here there is another pole, here there is other pole, and here there is other pole. So this is the polar plot of some open loop transfer function we are going to get in this format. Then if I stand here and if I see to my right side, the summation of the number of real open loop poles and real open loop zeros is equal to 1, is the odd number. So therefore this is present in the root locus. And if I stand here and if I see to my right side, then I can say the summation of the number of real open loop poles and real open loop zeros is 2, is an even number. So this is not present in the root locus. So only this part is present. So definitely we have 4 poles. So 4 poles means definitely we can say 4 poles means this is 4 poles means we can say 4 root locus values we are going to present. So they are going to come together and they are going to intersect, and all these things we are going to go to the infinity through the asymptotes. So we are going to have the 4 asymptotes. So this is going to come like this. So this is going to come like this, and this is going to come like this, and this is going to come like this, and this is going to come like this. So now you will see what is the thing here. If the average value of the real poles is equal to the real value of the complex poles, then it will have the 3 breakaway points. So listen carefully. If the average value of the real poles, so if you do the average value of this real poles, this one and this one, if you do the average, and if you are going to get the value which is equal to the real value of this complex poles, then we are going to have the 3 breakaway points we are going to get. So how we are going to get the 3 breakaway points? So first, still, these 2 things are going to get intersect. So first these 2 things are going to get intersect. So one breakaway point, again one branch will go up, other branch will go up. So here, like this they are going to go. And here this will intersect, here this will intersect. Again there will be another, like this we are going to get finally. So this is the way that we are going to get. So listen carefully. After draw the picture, then finally we are going to get in this format. So 3 breakaway points plus, like this we are going to get. So listen carefully. 3 breakaway points plus. So this is the one breakaway point, and here there is the another breakaway point. So here another breakaway point, other breakaway point. So total we have here one breakaway point, 3 breakaway point, and 3 breakaway points. So total we have 3 breakaway points. So therefore, if the average value of the real poles is equal to the real value of the complex pole, then it will have 3 breakaway points. But if the average value of the real poles is not equal to the real value of the complex pole, then we have only we can say only one breakaway point we are going to get. Only one breakaway point we are going to get. Then it will have only one breakaway point. So therefore we can say one breakaway point means how we are going to get the picture. Then here let me draw a picture again. Suppose there is a if the average value of the real force is not equal to the real value of the complex pole, then how we are going to get? So all these things are going to come like this. So these also come like this, and finally all will intersect at a common point, and then they will go in this format. So they will go in this format. So it will be like this, they are going to go. So this is one breakaway point. So you can see here there is only one breakaway point, but here we have 3 breakaway points. So therefore always you have to remember, if the average value of the real poles is equal to the real value of the complex pole, then it will have 3 breakaway points. If the average value of the real poles is not equal to the real value of the complex pole, then it will have only one breakaway point. So this is a graph for the corresponding 3 breakaway points, and this is a graph corresponding for 1 breakaway point. So this point always you have to keep in your mind. So these things always you have to keep in your mind. So therefore we can say that, simply we can say, if the average value of the real poles is equal to the real value of the complex pole, then we are going to have the 3 breakaway points, and this is a corresponding graph. And if the average value of the real pole is not equal to the real value of the complex pole, then it will have only one breakaway point, and this is a root locus graph for this corresponding thing. So finally I can say, if the average value of the real poles is equal to the real value of the complex pole, then it will have the 3 breakaway points, and the corresponding graph is this one. Suppose if the average value of the real poles is not equal to the real value of the complex pole, then it will have only one breakaway point, and the corresponding graph for this is this one. So now the next one is e to the power of minus ts is nearly equal to 1 minus st. So this is a standard thing always you have to keep in your mind. So basically this is very much useful in the control system. E to the power of minus ts is nearly equal to 1 minus st. So this is a very important equation. Definitely you will see this type of equations in the examination. So always you have to remember, e to the power of minus ts is nearly equal to 1 minus st. So this point always you have to keep in your mind. So therefore we can say e to the power of minus ts is nearly equal to, so e to the power of minus ts is nearly equal to 1 minus st. So this point always you have to keep in your mind. So therefore we can say e to the power of minus ts is nearly equal to 1 minus st. E to the power of minus ts is nearly equal to 1 minus st. So this point always you have to keep in your mind. So therefore we can say e to the power of minus ts is nearly equal to 1 minus st. So e to the power of minus ts is nearly equal to 1 minus st. So e to the power of minus ts is nearly equal to 1 minus st. So this is a very standard equation always you have to keep in your mind. So e to the power of minus ts is nearly equal to 1 minus st. So finally I can say e to the power of minus ts is nearly equal to 1 minus st. So now the next one is, if the pole or zero in the axis of H plane, we call it as a non-minimum phase system. If pole or zero in the axis of H plane, then we call it as a minimum phase system. So basically, what is the minimum? Here we are going to see the difference between the non-minimum phase system and the minimum phase system. So if you see any pole or zero in the axis of H plane, then we can say it is said to be non-minimum phase system. If all the poles and the zeros, if they are going to lie only in the axis of H planes, then we say it is a minimum phase system. So listen carefully. If all the poles and all the zeros, if they are going to lie in the axis of H plane, then we call this as the minimum phase system. If at least one of the pole or one of the zero, if it is lying in the axis of H plane, then we call it as a non-minimum phase system. So this one always you have to keep in mind. So we can say, if all the poles and the zeros, if they are going to lie in the axis of H plane, then we call it as a minimum phase system. If at least one of the pole or zero is going to lie in the axis of H plane, then we call it as the non-minimum phase system. So this one always you have to keep in your mind. So in simple words, I can say like this. If all the poles as well as the zeros, if they are going to lie in the midst of phase plane, then we call it as the minimum phase system. If at least one of the pole or at least one of the zero, if it is going to lie in the midst of phase plane, then we call it as the non-minimum phase system. So finally I can say, if all the poles are the zeros, if all the poles as well as all the zeros, if it is going to lie in the midst of phase plane, then we call it as the minimum phase system. If at least one of the pole or at least one of the zero, if it is lying in the surface plane, then we call it as the non-minimum phase system. So now let's go for the another concept. Listen carefully. So the phase angle of g of s into h of s at omega tends to infinity is equal to minus of e minus z into 90 degree for minimum phase system. Whereas the phase angle of g of j over h of j omega as omega tends to infinity is not equal to minus of p minus z into 90 degree. So this one always you have to keep in mind. So basically, suppose if they're asking for a minimum phase system. So for a minimum phase system, we can exactly say what is the phase angle of g of s h of s as omega tends to infinity is always equal to minus of p minus z into 90 degree. So how to remember this one? How to remember this one? Shortcut I have already told you. Suppose for a given open loop transfer function, there are p poles and there are z zeros. So each pole is going to give an angle of minus 90 degree, whereas each zero is going to convert an angle of 90 degree. So if you simplify, what you are going to get in this formula, which is minus p plus z into 90 degree also you can write. Or you can write it in the other fashion also. If you take minus common, we are going to get p minus z into 90 degree also you can write. You can write in any fashion, still we are going to get the same result. So for a minimum phase system, we can exactly say what is the phase angle of g of s h of s as omega tends to infinity, because there are p poles in the open loop transfer function and there are z zeros in the open loop transfer function. So each pole is going to contribute a phase angle of minus 90 degree and each zero is going to contribute a phase angle of 90 degree. So if we simplify, we are going to get minus p plus z into 90 degree, and if we take minus common, then we are going to get minus of p minus z into 90 degree. Suppose if they are asking the what is the slope of the, what is the final slope of the g of s h of s at omega tends to g infinity. So what is the final slope of g of s h of s at omega tends to infinity in the case of Bode plot? It also same thing. There are p poles and there are z zeros. So each pole is going to contribute an angle of minus 2 decimals per decade, and each zero is going to contribute an angle of plus 2 decimals per decade. So how we are going to get now? So minus p plus z into 20 decimals per decade, or if you take minus common, then we are going to get p minus z into minus 20 decimals per decade. In any way you can write, hoping we are going to get the same result. So this we can say in exact manner. For non-minimum phase system, these are not valid. So these equations are not valid. So we cannot say what is the value. They are going to get changes. So therefore we can say for a minimum phase system, we can exactly say what is the phase angle of g of s h of s at omega tends to infinity, and what is the slope of the g of s h of s. This what is the slope of the Bode plot at omega tends to infinity. We can exactly say for the minimum phase system, but we can't say for the non-minimum phase system. So finally I can say, so for a minimum phase system, we can exactly say what is the phase angle of g of s h of s as omega tends to infinity, and also what is the slope of the Bode plot when omega tends to infinity. This we can say easily for a minimum phase system with the above formulas, which is for p poles. So for a p poles, it is going to contribute minus 90 degree, and for z zeros it is going to contribute 90 degree. So if we simplify, we are going to get this equation. And if you want the slope means there are p poles, is going to contribute each pole of minus 1 decimals per decade, and there are z zeros, and each zero is going to contribute slope of plus 2 decimals per decade. If we simplify, we are going to get p minus z into minus 1 decimals per decade. So for a minimum phase system, we can exactly say what is the phase angle of g of h of s at omega tends to infinity, and also what is the final value slope of the Bode plot as omega tends to infinity. We can easily say with the help of these equations, but we can't say for the non-minimum phase system. So now the next concept is, in the proportional controller, there is always steady state error in the output. So if you are going to use the proportional controller in a control system, always we are going to have some finite value of the steady state error. So steady state error will be always equal to finite value. Whenever we are going to use a proportional finite value, whenever we are going to use a proportional controller in a control system. So therefore we can say in a proportional controller there is always steady state error in the output. So therefore we can say if you are going to use a proportional controller in a control system, always we are going to get some finite steady state error. We are always going to get means we are going to get some value. So in the case of proportional controller, there is always some steady state error in the output. So steady state error is always a finite value in the case of proportional controller. So this point always you have to keep in your mind. So therefore we can say in simple words. So therefore we can say in simple words that always you have to keep in your mind, which is basically we can say that the for a so if you are going to use a proportional controller in the case of control system, then always there is some finite steady state error you are going to get here. So this point always you have to keep in your mind. So therefore we can say whenever we are going to use the proportional controller in a control system, there is always steady state error is always going to present in the output, and the steady state error value is always equal to finite value. In integral controller, response slowly catches the desired input, and also steady state error is 0. Suppose if you are going to use the integral controller, then the response is going to slowly catches the desired input, and it is basically and steady state error is equal to 0. So always the steady state error is equal to 0 if you are going to use the integral controller. So this one always you have to keep in your mind that the response is going to very slowly it is going to catch the desired input. So in the case of integral controller, the response is going to slowly catches the desired input. Desired input is nothing but it is a desired output that we require. And also the steady state error is always equal to 0 in the case of integral controller. So therefore we can say in the case of integral controller, the response is going to always slowly catches the desired input. So therefore the steady state error will be always equal to 0. In the case of derivative controller, it doesn't respond to sudden errors. It doesn't eliminate the steady state errors, but it is going to improve the triangle state characteristics of the system. So in the case of derivative controller, it doesn't respond for the sudden errors. It doesn't eliminate the steady state error, and it is going to improve the triangle state characteristics of the system. It is going to decrease the rise time. It is going to decrease the rise time, and the steady state error will be always non-zero. Steady state error will be always non-zero. It is basically it is not equal to 0 in the case of derivative controller. So you can say in the case of derivative controller, it doesn't respond for the sudden errors. It doesn't eliminate the steady state errors, but it is going to improve the triangle state characteristics of the system. So you can say in the case of derivative controller, it doesn't respond for the sudden errors. It doesn't eliminate the steady state errors, but it is going to improve the triangle state characteristics of the system. Is the rise time is going to get decreases, and the steady state error value is always not equal to 0, means it is always equal to a finite value. So in simple words, I can say that in the case of proportional controller, there is always some finite steady state value error in the output. This steady state error will be always equal to finite value. But if you are going to use an integral controller, the response is going to slowly catches the desired input, and the steady state error is always equal to 0. But in the case of derivative controller, basically it doesn't respond for the sudden errors, and it doesn't eliminate the steady state errors, but it is going to improve the transient response characteristics of the system. Is the rise time is going to get decreased, and the steady state error will be always a finite value. So the next concept is by introducing the rate controller or the tachometer feedback in a second order system. So by introducing the rate controller or the tachometer feedback in second order system, then what is going to happen? Suppose if we are going to introduce the rate controller or the tachometer feedback in second order system, then what is going to happen? If the overall W will increase and time constant, the time constant for second order system is T is for number beta omega n. So as eta increases, T is going to get decreases. Whereas omega n is always equal to constant, and the steady state error is also going to get increases. So whenever you are going to introduce a rate controller or the tachometer feedback in a second order system, then the overall amplitude ratio will increase, and time constant is equal to 1 by zeta omega n for a second order system. As zeta increases, the time constant will decrease. Omega n will be always equal to constant, and the steady state error is also going to increases. So these are the effects that you can see whenever we are going to introduce a rate controller or the feedback, or you can say the rate controller or tachometer feedback in the case of second order system. So we can say by introducing the rate controller or a tachometer feedback in the case of second order system, the overall damping ratio will increase. So time constant for the second order system is equal to 1 by zeta omega n. As zeta increases, C will decrease, and omega n is equal to constant, and also the steady state error is also going to get increase. So now the next concept is with the introducing of PD controller in the second order system. So we can say with the introducing of PD controller in second order system. So suppose if we are going to introduce the PD controller in the second order system, then what are the things that are going to get occurred, that we will discuss in a very detailed manner. So listen carefully. So if you are going to introduce a PD controller in the second order system, then what are the effects that are going to happen? So these are all the effects that are going to happen because of this PD controller. Whenever you are going to introduce the PD controller in the second order system. So what are the things? So I already told you PD is proportional derivative. So it is going to improve the characteristic characteristics, means the rise time is going to get decreased. And you know the rise time of the balance is always equal to constant. So as the rise time decreases, means balance should increase, and only the rise time of the balance is equal to constant. And as the rise time decreases, means what we can say? As the rise time decreases, means simply we can say that the value of zeta will increase. The value of zeta will increase. The value of zeta will increase, because as the rise time decreases means the zeta will basically increases. The zeta will basically increases. The zeta will basically increases. And the omega is always equal to constant. And the peak quotient will decrease, because zeta and peak quotient are always inversely proportional. As the zeta increases means the peak quotient will decrease. So basically we can say both are inversely proportional. As zeta increases means the peak quotient will decrease. And ESS, steady state error, it will have some finite value always. So always we are going to get some steady state error, always finite value we are going to get. It is going to increase the stability of the system, and it is going to amplify the noise. So the signal to noise ratio will decrease. So basically PD is proportional derivative. So there is a derivative is there. So derivative is always going to amplify the noise. So because of this, signal to noise ratio will decrease, because as the noise is going to get increases, so overall signal to noise ratio will decrease. It is going to increase the stability of the system. This PD control is basically increase the stability of the system. It is similar to phase-led compensator. I already told basically PD control is nothing but it is a phase-led compensator, because phase-led compensator is also basically used to improve the transit character of the system. So phase-led means I can say 0 is closer to origin when compared to pole. So we are going to get a high pass filter. So first we are going to get a 0. 0 means plus 2 decibels per decade. Then we are going to get the slope pole minus 2 decibels per decade. So plus 2 minus 0 dB. So we are going to get a high pass filter. It doesn't change the type and the order of the system. So basically, by introducing the PD controller, it is not going to change. It is not going to change any type or the order of the system. So type as well as the order of the system will remain same as it is. Because PD means we can say PD was the transfer function of PD. So let me assume some K2 plus Ki into Kd into S. This is the transfer function of the transfer function of the PD controller. So by this, the type is not going to get changes, and the order of the system is also not going to get changes. So PD, Pi and PID have the high sensitivity. So it is able to respond to even small changes in errors. So basically, this PD, Pi and PID has a high sensitivity, and these are basically ability to respond even to small changes in errors, because these errors are given as an input to these controllers. So based on this, they are going to do some modifications, and they are going to give the output. So therefore, finally we are going to get the output as a steady state, is the actual output that we require, that we can easily get with the help of these controllers. So we can say, by introducing the PD controller in the second order system, basically PD controller means it is the phase-led compensator. The shortcut is what I told you. Here D means here also D. In the real there is a D, there is a D. So basically it is going to improve the transient characteristics of the system. Transient characteristics means the rise time is going to be decreased, means so that the response will increase. So rise time to bandwidth is always equal to constant. So as the rise time decreases, bandwidth will increase. And the zeta value is also going to get increased. The damping ratio is also going to get increased. So I've already told you as the zeta and the equals to vice versa, or inverse the proportion. As zeta increases, the proportion will decrease. And omega is always equal to constant. And always we are going to have some finite steady state error. It is always going to improve the stability of the system. And the derivative is there, it is going to amplify the noise of the signal. So based on the signal to noise ratio will decrease, because as the noise increases, so the derivative increases, so overall signal to noise ratio will decrease. It is basically similar to phase shift compensator and is a high pass filter. This one I already told you. And it doesn't change the type as well as the order of the system. It doesn't change the type as well as the order of the system. It will remain as a previous case. So PD, PI and PID have the high sensitivity. So these are the ability to respond to even small changes in errors. So based on this, they are going to give output in order to get the actual output as a desired output. So these are the things regarding the PD controller. Now let's go for with the introduction of the PI controller in a secondary system. Suppose if I am going to introduce the PI controller in a secondary system, then what are the effects that we are going to get here? So now here PI controller means it is basically phase lag compensator. It is going to improve the steady state response. So therefore, the rise time decreases means the rise time will increase, both are vice versa. So now, as the rise time increases means the bandwidth will decrease. So there also damping ratio increases, here also damping ratio increases. Same thing. There also damping ratio increases, here also damping ratio will increase. So I already told zeta and P4 should both are prime or inversely proportional. So as the zeta increases, NP will decrease. It is same in both the cases. But here always the steady state error is always equal to 0 in this case. So here always the steady state error is always equal to 0 in this case. So this is a point always you have to keep in your mind. So here the steady state error is always equal to 0 in this case. In this case, because it is going to decrease the steady state error, so yes as well is equal to 0. It decreases the stability of the system. Because see, by using the PI controller, we are going to have a lot of integrators. So as the integrators are increased, the stability will decrease. I means integrator. So whenever because of integrators, poles are going to happen. So poles are going to happen means the stability will decrease. See, because of PD, we are going to have zeros. So zeros is going to increase the stability of the system. Whereas with the help of integrators, we are going to get the poles. So because of this, the stability will decrease. I already told you. For root locus, if you are going to add the zero, the stability will increase because the return is going to shift to the ellipse of the explain. By adding the pole to the overall transfer function, then the stability will decrease because the return is going to shift to the axis of explain. Here also, with the help of PD, here in the case of the previous case, in the case of PD, always we are going to add the zeros, so the stability of the system will increase. But with the help of integrators, we are going to add the poles. So based on this, we can say the stability will decrease. So it is going to decrease the stability of the system. And its ability to noise ratio will increase. It is improved when compared to previous case. Here there is an integrator. So in the previous case, signal to noise ratio will decrease, and here it is the opposite. Signal to noise ratio will increase here. So it is similar to phase lag compensator as well as low pass filter. I already told you this one. So it is basically similar to phase lag compensator as well as low pass filter. So the lag compensator, we can say the lag compensator 0, but the pole is equal to origin when compared to 0. So pole means we are going to measure the principles for decay, and then we are going to have a 0. So measure the percentage of 0 dB. So we are going to get a low pass filter. It increases both the type as well as the order of the system by 1. So with the help of PI, we are going to both the type as well as the order of the system is going to increase by 1 because the denominator we are going to get increased. As you can see in the case of PI controller, what is the PI transfer function, which is KP plus KI by S. So basically, we can say the type as well as the order of the system is going to increase by 1. So these are the things always you have to keep in the mind. So ED, PI, PID have the high sensitivity. So they have the ability to respond to even small changes in error. So they can give the output modifications in order to get the actual value of the output as a desired value of the output. So I can say in simple words, with the introduction of so by introducing the PI control in the second order system, as I already told you, PI control is something that it is similar to phase lag compensator. So it is going to improve the steady state response. So steady state error is equal to 0. Their rise time is decreased, means the rise time will increase. So as the rise time increases, the bandwidth will decrease. Because of this, because of the controller, the rise time will increase. So as the rise time increases, bandwidth will decrease because the rise time and bandwidth is always equal to constant. So there is a zeta will increase, here also zeta will increase. So zeta will increase. So zeta and the peak output are inverse proportional. So therefore the peak output will decrease. And I have already told you the size of it is always equal to 0. And I already told you with the level of PI controller, we are going to have more number of poles. So because of this, the stability will decrease. So it is going to decrease the stability of the system because more number of poles have been added. So as the signal to noise ratio will increase in this case, it is going to get improved in this case. It is opposite to the previous one. It is basically similar to the phase-lag compositor as well as the low-pass filter, and it is going to increase both the type as well as the order of the system by 1. So because here Kb plus Ka by S is the transfer function of the PI controller, so because of this, the pole is increased by 1, the pole is increased by 1, so therefore we can say the type is increased by 1 as well as the order of the system is also increased by 1. So this is all about the PI controller. Now we are going to discuss the another point, which is with the introducing of the PID controller in the second order system. So basically, suppose if you are going to introduce the PID controller in a second order system, then what are the things that are going to affect that we are going to see? So PID is nothing but we can say it is a lag gate capacitor. So therefore we can say, see, I have already told you the lag gate capacitor is basically it is going to improve both the transient response as well as the steady state response. So these things I have already told you so many number of times. So PID controller is nothing but it is a lag gate capacitor. It is going to improve both the transient response as well as the steady state response. So transient response increase means the rise time is going to get decreased. So therefore the speed of the response will increase. And I have already told you the rise time and the bandwidth is always equal to constant. So as the rise time decreases, so definitely the bandwidth must increase, then only the plot is equal to constant. And the damping ratio, in all the three cases, whether you are going to use the PD controller or the PI controller or the PID controller, always the damping ratio is going to get increased. So whenever the damping ratio increases, MP will decrease because we can say the peak overshoot and the damping ratio are inversely proportional. So if one is going to increase, the other will decrease. And I have already told you the PID controller is also going to improve the steady state response, means the steady state error will decrease. So therefore we can say the steady state error will be 0. It is similar to lag gate compensator, or you can say it is a band reject filter. So I have already told you this is basically it is similar to lag gate compensator and is also called as the band reject filter. This one I have already told you. It is going to improve both the transient response as well as the steady state characteristics. So therefore we can say it is going to improve both the transient characteristics of the system as well as the steady state characteristics of the system. It is going to increase both the type as well as the order of the system by 1 unit. So I have already told you it is going to increase both the type as well as the order of the system by 1 unit. Why it is like this? Because PID means here we are going to have proportional integration derivative. So what is the transfer function you are going to get for the PID controller? So here I am going to write which is Kp proportional plus here I can say Ki by S plus Kd into S. So because of this S, definitely the type is going to increase by 1 unit, and because of this the order is also going to get increased by 1 unit. So these are the things always you have to keep in your mind. So therefore we can say by introducing the PID controller in the second order system, it is going to improve both the transient response as well as the steady state response. Increasing the transient response means it is going to decrease the rise time. So as the rise time decreases, bandwidth will increase because the rise time demand is always equal to constant. In all the three cases, the damping ratio will always increase. So because of this, the peak overshoot will decrease because the damping ratio and the peak overshoot are inversely proportional. And this PID is also going to improve the steady state response. The steady state error will decrease. The steady state error is equal to 0. So we can say it is similar to lag gate compensator. We also call it as a band reject filter. So it is going to improve both the transient state characteristics as well as the steady state characteristics. And it is going to increase both the type as well as the order of its control system by 1 unit. So this one I already told you so many number of times. So this data always you have to remember for PD controller, PI controller as well as the PID controller. So therefore definitely you are going to see at least one question from this concept. So the next point is the polar plot. So polar plot we are going to study. So what is the polar plot? I already told you, it is the graph of the magnitude of the open loop transfer function versus the phase angle of the open loop transfer function. So basically here, the g of s, h of s magnitude versus g of the phase angle of g of s, h of s when the value of omega is varying from 0 to infinity. So here always g of s, h of s. So therefore, the polar plot is nothing but it is a basically magnitude and the phase angle plot. So magnitude means the magnitude of g of s, h of s versus the phase angle of g of s, h of s, where omega is varying from 0 to infinity. So this is called as the polar plot. So polar plot means it is a graph between the magnitude of the open loop transfer, the magnitude of the open loop transfer function versus the phase angle of the open loop transfer function, and the omega is varying from 0 to infinity. So therefore we can say the magnitude of g of h of s versus the phase angle of g of h of s, where the value of omega is varying from 0 to infinity. So I've already told you with the help of polar plot only we are going to draw the Nyquist plot. I've already told you this one, just we are doing that. With the help of polar plot we are going to get the Nyquist plot also. I've already told you. So now what is the Bode plot? Bode plot is nothing but in the Bode plot we are going to have the two plots. One is the magnitude plot and the other is the phase angle plot. So magnitude plot means it is the magnitude is basically in terms of dB. So 20 log of mod of g of s, h of s with the base 10 versus log of omega, and the phase angle is the phase angle of g of s, h of s versus log omega when the value of omega is varying from 0 to infinity. So in the case of the Bode plot we are going to have the two plots. One is the magnitude plot and the other is the phase angle plot. So magnitude plot basically in terms of dB we are going to calculate. So therefore 20 log of mod of g of j omega h of j omega with the base 10 versus log of omega with the base 10, and the phase angle plot is the phase angle of g of s, h of s versus log omega with the base 10 when the value of omega is varying from 0 to infinity. So now the next concept is, I already told you for e to the power of minus ts, I already told you for e to the power of minus ts the magnitude is always 1 and the phase angle is minus omega t radians. This is in terms of radians, but if you want the in terms of degrees, then it is 1 at an angle of minus 57.3 omega t degrees. This one I've already proved also. I've already basically this one proved also in my formulas class. So therefore we can say, see basically j is nothing but j omega. So e to the power of j theta, here theta is equal to, we can say minus omega t. So therefore 1 at an angle of theta, 1 at an angle of theta is now minus omega t. This is in terms of radians, but if you want in terms of degrees means here you have to include 57.3. This is the only factor we have to include in order to convert the radians to degrees. I've already proved this one also. I've already proved in my class, in my formulas class. So therefore we can say e to the power of minus ts. This is in terms of the, basically we can say this we can write in terms of polar forward, which is 1 at an angle of minus omega t radians. And if you want to write in the terms of degrees, then it is equal to 1 at a phase angle of minus 57.3 omega t degrees. So now the next one is type of the system will tell us where the plot will begin at omega is equal to 0, and the order of the system will tell us where the plot will end, means at omega is equal to infinity. So I already told you, if you want to basically draw the polar plot, the first thing that you have to see is the open loop transfer function. So basically, if you want to draw the polar plot, first thing is that you have to see is the open loop transfer function. So the type of the system is going to tell you where the plot is going to get begin, and the order of the system is going to tell you where the plot is going to get end. So listen carefully. I've already told you with the help of open loop transfer function only we are going to draw the polar plot. So just by knowing the two important things, which is the type of the system and the order of the system, we can say where the plot is going to begin and where the plot is going to get end. So therefore we can say the type of the system is going to tell you where the polar plot will begin, means at omega is equal to 0, and the order of the system will tell us where the plot will end, means at omega is equal to infinity. So this one always you have to keep in your mind. So therefore we can say the type of the system will tell us where the polar plot will begin at omega is equal to 0, and order of the system will tell us where the plot will end, means at omega is equal to infinity. So listen some more things here. See type 0. Type 0 means we can say for a type 0 system, when omega is equal to 0, the phase angle of g of j omega h of j omega is equal to 0 degree. Suppose for type 1 system, when omega is equal to 0, the phase angle of g of j omega h of j omega is equal to minus 90 degree. Whereas for the type 2 system, when omega is equal to 0, the phase angle G of J omega H of J omega is equal to minus 180 degree. And for type 3 system, when omega is equal to 0, the phase angle of G of J omega H of J omega is equal to minus 270 degree. So this I've already told you open loop transfer function. Suppose open loop transfer function G of S H of S is equal to, suppose let me in this format which is S to the power of P, is the power of P. Suppose if P is equal to 0, then we say it is a type 0 system, then definitely what is the phase angle we are going to get 0. Suppose for type 1 system is P is equal to 1, then what is the phase angle you are going to get minus 90 degree. So P is equal to 1 means 1 by S. So 1 by J omega is 1 by phase angle 90. If you put upward, you are going to get minus 90. So therefore we can say for type 2 system, when omega is equal to 0, the phase angle of G of J omega H of J omega is equal to minus 180 degree. And for type 3 system, when omega is equal to 0, the phase angle of G of J omega H of J omega is equal to minus 270 degree. Type 4 means again it is 0 degree. So same thing it is going to repeat. So type 4, let me write here. So type 3, then type 4 means here. You have to go here again. Type 4, type 5, type 6, type 7, again type 8. So same thing it is going to repeat in the sequence. In this manner only it is going to repeat. Type 0, type 1, type 2, type 3, then type 4, type 5, type 6, type 7. Like that it is going to repeat. So for type 0 system, when omega is equal to 0, the phase angle of G of S H of S is equal to 0 degree. For type 1 system, when omega is equal to 0, the phase angle of G of S H of S is equal to minus 90 degree. And for type 2 system, when omega is equal to 0, the phase angle of G of J omega H of J omega is equal to minus 180 degree. And for type 3 system, when omega is equal to 0, the phase angle of G of J omega H of J omega is equal to minus 270 degree. So now suppose for order 1, for order 2, for order 3 and order 4, see basic type of system is going to tell you where the plot is going to become, where the plot is going to get begin, and order of system is going to tell you where the plot will end. Suppose for order 1 system, when omega is equal to 0, the phase angle of G of S H of S is equal to minus 90 degree. And for order 2 system, when omega is equal to infinity, the phase angle of G of H of S is equal to minus 180 degree. And for order 3 system, when omega is equal to infinity, the phase angle of G of H of S is equal to minus 270 degree. And for order 4 system, when omega is equal to infinity, the phase angle of G of H of S is equal to minus 360 degree. So order 5 means again it is going to repeat in this manner. So it is going to repeat. So this one always you have to keep in your mind. So now always remember the type of the polar system will give the information where the polar plot is going to get begin at omega is equal to 0, and the order of the system is going to tell you where the polar plot is going to get end is at omega is equal to infinity. So now based on this information, now we are going to draw some graph. So if you remember this graph, you can draw the polar plot in a very fraction of second. So this concept already I told you, but let me repeat. So this is the S plane. So I've already told you this is type 0, this is type 1, this is type 2, this is type 3. Now then type 4 means again repetition. Same repeating here. Type 4, type 5, type 6, type 7. Similarly here order 1, order 2, order 3, order 4. So again order 5, order 6, order 7. Again it is going to repeat. So therefore we can say for type 0 system, the phase angle of G of S, H of S at omega is equal to 0 degree. And for type 1 system, the phase angle of G of H of S at omega is equal to minus 90 degree. And for type 2 system, the phase angle of G of H of S at omega is equal to minus 180 degree. And for type 3 system, the phase angle of G of H of S at omega is equal to minus 270 degree. Same thing is going to repeat again. And for order 1 system, the phase angle of G of H of S at omega is equal to minus 90 degree. And for order 2 system, when omega, the phase angle of G of H of S at omega is equal to minus 180 degree. And for order 3 system, the phase angle of G of H of S at omega is equal to infinity is equal to minus 270 degree. And we can say for order 4 system, the phase angle of G of H of S at omega is equal to infinity is equal to minus 360 degree. So same thing we are going to get here. So if you remember this one, it is very easy. It is very easy to draw the polar plot in a very fraction of seconds. And I already told you this graph is going to only for 2. We can say that the important points regarding this is that all the poles are going to lie in the S of S plane. That is the one concept. And basically we have not included any zeros. Suppose if you are going to include the zeros, then the graph is going to, the plot of the graph will be same, but the ending and the starting points are going to get different. So this one I've already told you. So the plot of the graph will be same, but the starting and the ending points are going to get changed. So this one I've already told you. So therefore, type 0, type 1, type 2, type 3, again type 4, type 5, so it is going to repeat order 1, order 2, order 3, order 4, again order 5, again it is going to get repeat. So these things always you have to keep in your mind. We can say, except the type 0, all the polar plots are going to start from the infinity at omega is equal to 0. I've already told you. So except type 0, type 0, all the polar plots are going to start from infinity at omega is equal to 0. So what I am trying to tell you, except type 0, the remaining all other polar plots are going to start from infinity at omega is equal to 0. So then what is going to happen for type 0 system? For type 0 system at omega is equal to 0, it is going to have a finite magnitude value. Listen carefully. For type 0 system at omega is equal to 0, it is going to have a finite magnitude value. Whereas we can say for remaining all other systems, for remaining all other type systems at omega is equal to 0, its value, the magnitude value is always equal to infinity. So that is the reason they are going to start from infinity. So listen carefully. For type 0 system, at omega is equal to 0, we are going to get the magnitude as finite value. So that is the reason it is going to start from a finite value. Whereas all other type system except type 0, at omega is equal to 0, it is going to have the magnitude value is equal to infinity. So because of this reason, they are going to start from infinity. So therefore we can say, except type 0, all other polar plots are going to start from infinity at omega is equal to 0. Whereas a type 0 system at omega is equal to 0, it is going to start from a finite value. So listen carefully. Except type 0, all other polar plots are going to start from infinity at omega is equal to 0. Whereas the type 0 system at omega is equal to 0, it is going to have a finite magnitude value. So now the next point is, polar plots are not closed paths, whereas the Nyquist plots are the closed paths. And what I told you, so polar plots are not closed paths, or we can say open plots, whereas the Nyquist plots are the closed paths. So therefore we can say polar plots are not closed paths, whereas the Nyquist plots are the closed paths. This I already told you. With the help of the polar plot, we are going to draw the Nyquist plot. I already told you. So therefore, with the help of four regions, we are going to get a Nyquist plot. I already told you. So therefore, we can say polar plots are not closed paths, whereas the Nyquist plot are the closed paths. The next point is, a point is said to be enclosed by a contour or an open path if it is lies to the right side to the direction of the contour. So listen carefully. What is the meaning of this statement? Suppose there is some contour like this. Suppose there is some contour in this direction, omega is equal to 0 to omega is equal to infinity. Suppose this is a point here. So this is a point here. So you can, this point is to the right side of this path. So therefore we can say this path is enclosed by this contour. So a path is said to be enclosed by a contour or open path if it is going to lie to the right side to the direction of the contour. So you can say clearly. So suppose this is some polar plot from omega is equal to 0 to omega is equal to infinity. So this is the direction of the increasing value of omega. So now this is the point P. So this point P is to the right side of this contour. So therefore we can say this point is enclosed by this contour. So therefore we can say a point is said to be enclosed by a contour or the open path if it is lies to the right side to the direction of the contour. The next point is, a point is said to be encirclement if the point lies inside the closed curve and the point is said to be enclosed if lies right side to the direction of the closed curve. Listen carefully. A point is said to be encirclement if the point lies inside the closed curve and the point is said to be enclosed if it lies to the right side of the direction of the closed curve. Same thing as the previous one. See, I have already told you. Suppose in the Nyquist curve, suppose if you take any point in the Nyquist curve, in the Nyquist plot, if you take any point and from that point draw a straight line in any direction, and if you are going to get a n value, some non-zero value. So some curves are clockwise, some curves are anti-clockwise, and I've already told you anti-clockwise take it as positive and clockwise take it as negative. So if you, after doing addition, if you are going to get some non-zero value, means yes, that point is said to be enclosed by the Nyquist plot, or we can say if the point is going to lie to the right side, if the point is going to lie to the right side of the encirclement, then we can say the point is enclosed. So listen carefully. A point is said to be encirclement if the point lies inside the closed curve, and the point is said to be enclosed if lies right side to the direction of the closed curve. And I already told you, suppose if you take a Nyquist plot, it's a closed curve. So from that point, suppose I want to know whether this point is enclosed by this curve or not. So from that point, draw a straight line in any direction, and if you are going to get the value of a non-zero, because the clockwise have taken negative, anti-clockwise is positive. So after doing the summation, if you are going to get a non-zero value of n, then we can say that point is said to be encircled by the contour. So we can say a point is said to be encirclement if the point lies inside the closed curve, and the point is said to be enclosed if lies to the right side to the direction of the closed curve. The next point is if polar plot not encloses -1 plus j0, then the system is stable. If the polar plot cuts the -1 plus j0, then the system is marginally stable. If the polar plot encloses the -1 plus j0, then the system is unstable. This concept I already told you. So whenever the polar plot is going to enclose the -1 plus j0, then we can say the system is said to be stable system. So gain crossover frequency is lesser than phase crossover frequency. Suppose if the polar plot is going to cut the -1 plus j0, then we can say the system is said to be marginally stable. Means we can say that basically we can say the system is said to be marginally stable. If the means the gain crossover frequency is called phase crossover frequency. If the polar plot encloses the -1 plus j0, then the system is said to be unstable system. Means the gain crossover frequency is greater than the phase crossover frequency. So finally I can say if the polar plot is not going to enclose the -1 plus j0, then we can say the system is said to be stable. Means the gain crossover frequency is lesser than phase crossover frequency, and the gain margin is positive, and the phase margin is also positive. If the polar plot is going to cut the -1 plus j0, then we can say the system is said to be marginally stable. So gain crossover frequency is equal to phase crossover frequency, and also we can say that the gain margin is equal to 0, and the phase margin is also equal to 0. If the polar plot is going to enclose the -1 plus j0, then we can say the system is said to be unstable system. And also unstable system is the gain crossover frequency is greater than phase crossover frequency. And also one more important point, which is the gain margin is equal to negative, and the phase margin is also equal to negative. Shortcut to remember: suppose if you are eating anything, then you will become unstable, right? If you eat a lot of things, it will become unstable. If you are not eating, means you are very stable person. Same thing. If the graph is going to enclose the -1 plus j0, means it is unstable. If it is not enclosed, means it is a stable. It is shortcut to remember. Suppose if you are eating the food very heavy, and definitely you are going to become unstable. Same thing here also. If the -1 plus j0 is enclosed by the polar plot, means then the system is unstable. If it is not enclosed, means it is stable. So this is what I am trying to tell you. So now the next statement is: for minimum phase and non-minimum phase functions of any type and order, when zeros are present, it is necessary to check the intersection of the polar plot with the negative real axis between omega is equal to 0 and omega is equal to infinity. So listen carefully. For minimum phase system as well as the non-minimum phase systems of any type and order, when zeros are present, it is necessary to check the intersection of the polar plot with the negative real axis between omega is equal to 0 and omega is equal to infinity. So what I am trying to tell you, see, I have already told you some important graphs. There I have told you the different graphs I have shown you for the assumptions. All the poles are going to lie in S of S plane, and there are no zeros I am going to include. And these are the things I have already told you. Suppose if you are going to include the zeros, then what is going to happen? Then you need to check whether this polar plot is going to intersect any real axis, negative real axis or not. We need to compulsory check. So this is the point always you have to keep in your mind. So if you are going to include a 0 in a open transfer function, then compulsory you have to check whether this polar plot is going to intersect the real axis or not. We need to check it. So therefore we can say for minimum phase system as well as non-minimum phase systems of any type and order, when zeros are present, it is necessary to check the intersection of the polar plot with the negative real axis between omega is equal to 0 to omega is equal to infinity. So whatever the graphs I have shown you, those graphs under the assumptions all the poles are going to lie in the S of S plane and no zeros are included. Suppose if you are going to include the zeros, the first thing that you need to confirm is that whether this polar plot is going to intersect any real axis or not, that you need to check. So this is the point is going to tell you. Whether it is a minimum phase system or non-minimum phase system, always you need to check. If you are going to include a zero in the open loop transfer function, first thing that you need to check is whether this polar plot is going to intersect the negative real axis or not. We need to check. Next one is the gain margin is always inversely proportional to the gain of the system, and the phase margin is also inversely proportional to gain of the system. So as gain k increases, the gain margin decreases and the phase margin decreases. So we can say the system is said to be unstable. So this is a very important statement, always you have to keep in your mind. So we can say the gain margin is always inversely proportional to system gain, as well as the phase margin is also inversely proportional to system gain. So whenever the gain of the system increases, definitely the gain margin decreases as well as the phase margin decreases. So we can say the system is said to be unstable. Gain margin decreases means it will become negative. Phase margin decreases means it will become negative. So definitely we can say the system will become unstable. So therefore we can say the gain margin is always inversely proportional to system gain, and the phase margin is also inversely proportional to system gain. So as the gain of the system increases, the gain margin decreases and the phase margin decreases. So therefore the system will become unstable. So therefore we can say finally the gain margin is inversely proportional to system gain and the phase margin is also inversely proportional to system gain. As the system gain k increases, the gain margin is going to get decreases and the phase margin is going to get decreases. So therefore the system is going to become unstable. So unstable means as the gain margin decreases means it will become negative. Phase margin decreases means it will become negative. So therefore the system is going to become unstable. So this point always you have to keep in your mind. The next one is if g of s, h of s is a lead compensator, then always the polar plot of this will lie in the first coordinate. If g of s, h of s is a lag compensator, then the polar plot is always going to lie in the fourth coordinate. So this one I have already told you. So therefore we can say if g of s, h of s is a lead compensator means 0 is closer to origin when compared to pole, then we can say that polar plot is always going to lie in the first coordinate. Suppose if g of s, h of s is a lag compensator means the pole is closer to origin when compared to 0. So therefore we can say that the polar plot is always going to lie in the fourth coordinate. So finally I can say if the open loop transfer function is a lead compensator means 0 is closer to origin when compared to pole, then always the polar plot is going to lie in the first coordinate. And if the open loop transfer function is a lag compensator, then definitely the polar plot is going to lie in the fourth coordinate. So this point always you have to keep in your mind. So now the next concept is, so all these points always you have to keep in your mind. So therefore you can solve this type of questions in a very fraction of seconds. These are the important points here. So now the next point is in Manitowood-Bode plot diagram. So in the Manitowood-Bode plot diagram, initial slope of the line indicates the number of zeros or the poles which are going to present in the origin. So I already told you in the case of Manitowood-Bode plot diagram, just by seeing the initial slope, we can say how many number of zeros or how many number of poles which are going to present at origin, we can say easily. So therefore we can say that just by seeing the initial slope of the line, we can say how many number of zeros and how many number of poles which are going to present in the origin. The next point is the summation of all the slopes of zeros plus summation of all the slopes of poles is nothing but it is a last line slope in the Manitowood-Bode plot or slope of the highest frequency asymptote. So what is the meaning of this one? So I have already told you. Suppose in the open loop transfer function, let me assume there are z number of zeros. So each is going to give you each zero is going to give a slope of 20 decibels per decade. Plus, suppose there are p number of poles. So each pole is going to give a slope of minus 20 decibels per decade. So if you do like this, then you are going to get the highest frequency asymptote frequency. This is nothing but it is the highest frequency asymptote slope. So this is the highest frequency asymptotic slope. So therefore we can say that it is equal to last line slope in the Manitowood-Bode plot or the slope of the highest frequency asymptote. So we can say this is a last line slope in the Manitowood-Bode plot or the slope of the highest frequency asymptote. So this one always you have to keep in your mind. Same thing. summation of poles of all zeros plus summation of slopes of all poles is nothing but of the open loop transfer function is always equal to the last line slope in the mapped Bode plot or the slope of the highest frequency asymptote. So finally I can say that this formula always you have to keep in your mind, which is for a given open loop transfer function, the number of zeros are j into p0 is going to contribute a slope of plus 3 decimals per decade. And if there are p number of poles in the open loop transfer function, so each pole is going to contribute a slope of minus 3 decimals per decade. If you do this one, we are going to get finally the last line slope in the mapped Bode plot or the slope of the highest frequency asymptote. So now the next point is, if the starting slope is equal to minus 20 decimals per decade, we can say there is one pole at origin in the open loop transfer function. So we can say it is a type 1 system. Then always you have to remember the Kp is always equal to infinity and Ka is always equal to 0. So this one always you have to keep in your mind. So Kp is always equal to infinity and Ka is always equal to 0. Then what is Kv? Kv is nothing but extend the first line only until it cut the 0 dB line. And that frequency omega, then Kv is equal to omega. So basically what I am trying to tell you, see basically extend the starting line slope of minus 10 decibels per decade until that line is going to cut the 0 dB. So at this 0 dB, try to figure out what is the omega. That omega is nothing but Kv. So therefore we can say if the starting slope is equal to minus 3 decibels per decade, we can say there is one pole at origin. It's a type 1 system. So for type 1 system, so therefore Kp is equal to infinity and Ka is equal to 0 and Kv is nothing. See basically for type 1 system, basically for type 1 system, basically for a unit step input, what is the steady state error? 0, right? And for ramp input, what is the steady state error? It is A by Kv. And for we can say for this one, which is a parabolic input, what is steady state error? Is equal to infinity. So this I have already told you. If the steady state error is equal to 0 means what is the value of Kp? Kp is equal to infinity. Suppose this is infinity, this is infinity something, but we can say Ka is equal to 0. Then only you are going to get infinity. So this we can easily see here. So Kp is equal to infinity, Ka is equal to 0. But you are going to get this value 500 you are going to get. So what is the value of Kv? Kv is nothing but extend the first line only until it is going to cut the 0 dB line. And that frequency omega is nothing but Kv. So that frequency omega is nothing but Kv. So therefore we can say if the starting slope of the mapped Bode plot is equal to minus 10 decibels per decade, it indicates it is a type 1 system. So for type, as I have already told you, suppose if the starting slope is equal to minus 20 decibels per decade, means we can say there is one pole at origin. So therefore we can say it is a type 1 system. So now, as I have already told you, for type 1 system, the steady state error for the step input is 0 and the steady state error for the ramp input is A by Kv and the steady state error for the parabolic input is infinity. So from this we can say that Kv is nothing but infinity, then only A by 1 plus Kp. So A by infinity is equal to 0. Similarly here A by Kv is equal to 0 is nothing but Kv. A by Kv is equal to infinity means we can say what is the value of Kv? Kv is equal to 0. Sorry, Ka is equal to 0 because A by Ka. So as A by Ka is equal to infinity, so Ka is equal to 0. So now A by Kv, here we are going to get some finite value. So we have to find out what is the value of Kv. So Kv is nothing but extend the first slope line, means whatever the starting slope line minus the per decade, just extend this line until it is going to cut the 0 dB line. So at this 0 dB, what is the frequency? Just try to figure out from the mapped Bode plot. That frequency is nothing but Kv. That frequency is nothing but Kv. You substitute here and get the value of the steady state error for the ramp input. So now, suppose if the starting slope is equal to minus 40 decibels per decade, means there are two poles at origin. So therefore we can say type 2 system. So for type 2 system, I have already told you what is the steady state error. What is the steady state error for the unit step input, which is equal to 0. And what is the steady state error for the ramp input, which is 0. And what is the steady state error for the parabolic input, which is A by Ka. So if you see clearly, for step input, if the steady state error is equal to 0, Let's say by 1 plus Kp is equal to 0. So from this we can see what's the value of Kp? Infinity. So Kp is equal to infinity. Similarly, A by Kv is equal to 0. So what's the value of Kv? Infinity. So now we have to get the value of A by K. K value we need to figure out. So extend the first line only, and then it is going to cut the 0 dB line. And that frequency is called as omega. So K is equal to omega square. Here whatever is minus 4 response per decade at initial slope line, just extend that line until it is going to from the 0 dB. So what is the frequency of omega? Try to figure out from this manual Buddha law. But omega is nothing but kV. Kv is equal to omega square. So K is equal to omega square. So keep this here, you will get the steady state error for the parabolic input. So these things always you have to keep in your mind. So the next point is plus or minus 6n decibels per octave is always equal to plus or minus 20n decibels per decade. So this one always you have to keep in your mind, which is always plus or minus 6n decibels per octave is always equal to plus or minus 20n decibels per decade. So this is a formula always you have to keep in your mind, decibels per decade. So this formula always you have to keep in your mind. So plus or minus 6n decibels per octave is always equal to plus or minus 20n decibels per decade. So simply we can say 6 decibels per decade is always equal to 20 decibels per decade. So 6 decibels per octave is always equal to 20 decibels per decade. So attach plus or minus, attach n. So here we are going to get this one, which is plus or minus 6n decibels per octave is always equal to plus or minus 20n decibels per decade. So this one always you have to keep in your mind. So therefore we can say plus or minus 6n decibels per octave is always equal to plus or minus 20n decibels per decade. The next point is state variables defined for physical systems are known as the physical variables. So state variables which are defined for the physical systems which are known as the physical variables. Whereas the state variables which are defined for the differential equation representing the differential equation are known as the phase variables. So listen carefully. The state variables which are defined for the physical systems are known as the physical variables, whereas the state variables which are defined for the differential equation which is going to represent the physical system are known as the phase variables. So in simple words I can say, when the state variables are defined for the physical system, we say it as a physical variables. And the state variables which are defined for the differential equation which is going to represent a physical system, which are basically called as the phase variables. So in simple words I can say, if you are going to define a state variable for a physical system, it is called as a physical variables. But if you are going to define the state variables for a differential equation, then it is called as the phase variables. So finally I can say, if you are going to define the state variables for the physical system, it is called as the physical variables. If you are going to define the state variables for the differential equation, then it is called as the phase variables. So finally I can say, state variables which are defined for the physical systems are known as the physical variables, whereas the state variables which are defined for the differential equation which is going to represent the physical system are known as the phase variables. So these things always you have to keep in your mind. The next point is here, negative feedback in a control system. So we will discuss some important points regarding the negative feedback in a control system. Suppose if you are going to apply a negative feedback in a control system, then what are the things that are going to happen that we will discuss now. Overall gain is going to get decreases. I already told you, because overall gain is nothing but g of s, h of s, g of s by 1 plus g of h of s. Whenever you are going to apply the negative feedback, then what is overall gain? G of s by 1 plus g of s, h of s. So definitely we can say the denominator is going to get increases. So therefore the overall value is going to get decrease. Overall gain will reduce the overall gains, and it is going to improve the disturbance rejection. So it is going to improve the disturbance rejection, and it's going to reduce the sensitivity to the parameter distortion when compared to open loop system, and is going to increase the bandwidth. It is also going to reduce the output impedance, and also it is going to reduce the distortion, and is going to improve the system stability. So these are the things which are going to happen because of the negative feedback. So whenever you are going to apply negative feedback in control system, the overall gain is going to get decreases. Gain to bandwidth is always equal to constant. So as gain decreases, the bandwidth will increase, and it will improve the disturbance rejection, and it's also going to reduce the sensitive to parameter distortion when compared to open loop system, and also it is going to reduce the output impedance. It is going to reduce the distortion, and also it is going to improve the system stability. So these are the things which are going to happen because of negative feedback in control system. So finally I can say, whenever you are going to apply negative feedback in a control system, it is going to reduce the overall gain. So as the gain to bandwidth is always equal to constant, as the gain decreases, bandwidth will increase. So it is going to increase the bandwidth, and it is going to improve the disturbance rejection, and is also going to reduce the sensitivity to the parameter distortion, and is also going to reduce the output impedance. It is also going to reduce the distortion, and is also going to improve the system stability. So these are the things which are going to happen because of negative feedback. The next point is, when deriving the transfer function of a linear element, the initial conditions are assumed to be 0 and the element is assumed to be not loaded. So I already told you, whenever you are going to apply a transfer function, we are going to assume that all the initial conditions are 0. And also we say that the element is assumed to be not loaded. So therefore, these are the assumptions that we are going to take in whenever we are going to apply the transfer function concept. Means we are going to assume that initial conditions are 0 and also the element is not loaded. These are the assumptions that we are going to take in order to apply the transfer function. When deriving the transfer function of a linear element, the initial conditions are assumed to be 0 and the element is assumed to be not loaded. So this is the point always you have to keep in mind. So whenever we are going to apply the transfer function, always we have to assume that the initial conditions are 0 and also we can say the element is not loaded. So finally I can say, when deriving the transfer function of a linear element, the initial conditions are assumed to be 0 and the element is assumed to be not loaded. The next one is, natural time constants of the response depends only on the poles of the system. Natural time constants of the response depends only on the poles of the system. So natural time constants of the response is going to depend only on the poles of the system. So this one always have to keep in mind. So natural time constants of the response is going to depend only on the poles of the system. So this is a very important statement. So natural time constants of the response is going to depend only on the poles of the system. So this is a very, very important statement. So therefore we can say, whatever the natural time constants of the response, they are going to depend only on the poles of the system. So we can say, the natural time constants of the response, they are going to depend only on the poles of the system. It's a very, very important statement. So therefore, whatever the natural time constants of the response, they are going to depend only on the poles of the system. The next statement is, the characteristics of the closed loop systems are. So now we'll discuss some important characteristics of the closed loop systems, which are, it is going to compensate the disturbance, it is going to reduce the sensitivity of the plant parameter variations, it is going to involve the output measurement, it has the ability to control the system transient response. With an increase in the forward gain, the output value approaches to the input value in the case of negative feedback control system. So, the transfer function is dependent only upon its internal structure and the components and is independent of the input applied to the system. Listen carefully. Let me tell you some facts regarding the characteristics of the closed loop system. So, the characteristics of the closed loop systems are, it is going to compensate the disturbance, means it is going to compensate the, means it is going to reduce the disturbances. It is going to reduce the sensitivity of the plant parameter variations, means it is going to reduce the sensitivity of the plant parameter variations. It is going to involve the output measurements. In the case of closed loop systems, we are going to measure even the output also. It has the ability to control the system transient response. So we can easily control the transient response also. So with the help of closed loop, we can even control the transient response. With an increase in the forward gain, the output value approaches the input value in the case of negative feedback control system. Yes, I already told you. In the case of the, see, suppose if you are going to increase the forward gain, the output value is going to approach the input value in the case of negative feedback control system. So basically, suppose if you are going to increase the forward gain, then the output value is going to approach the input value only in the case of negative feedback system. So now, the transfer function is always independent, is dependent only upon its internal structure and components and is independent of the input applied to the system. So you know what is the transfer function? Laplace transform of output by Laplace transform of input. So that we are going to get some equation. If the equation is independent of the output or input, it is going to depend only on the parameters of the given system. So the transfer function is dependent only upon its internal structure and components and is independent of the input applied to the system. So whatever the transfer function of the system is going to depend only on the components and structures which are going to present in that system. It is independent of the type of the input that we are going to get applied. So irrespective of the input, the transfer function is same because the system is fixed. So if the system components are changed, means the transfer function is also going to get changes. So therefore we can say the transfer function is dependent only upon its internal structure and the components and is independent of the input applied to the system. So we can say finally the characteristics of the closed loop systems are, it is going to basically reduce the disturbances, it is going to reduce the sensitivity of the parameter variations, it is going to involve the measurement of output, and also it is able to even control the system transient response. So if you are going to increase the forward gain, then the output value is going to approach the input value in the case of negative feedback system. The transfer function is basically dependent only upon its internal structure and components, and it is independent of the input applied to the system. So the transfer function is basically independent of the type of the input that you are going to apply because it is only depending upon the structure as well as the components which are going to present in that. As the components and the structure and the components are going to vary, whenever the transfer function is going to get vary. Otherwise, it is fixed. So now the next point is bandwidth into rise time is always equal to constant and its value is equal to 0.35. So rise time is divided by second and bandwidth unit is hertz. So definitely hertz means 1 by second. So 1 by second of cancels. It is a unit phase. So we can say the unit of bandwidth is hertz and the unit of rise time is seconds. So like to write here, the unit of the bandwidth is equal to hertz and the unit of the rise time is equal to second. So these two things always you have to keep in your mind. So we can say the bandwidth of the unit of the bandwidth is hertz and the unit of the rise time is seconds. So when we are going to multiply this, we are going to get a constant which is unitless. So its value is equal to 0.35. So always remember bandwidth into rise time is always equal to 0.35. That is the reason bandwidth into rise time is always equal to constant. If bandwidth is increasing means rise time will decrease. If the bandwidth is decreasing means the rise time will increase because the plot is always equal to constant and the unit of bandwidth is hertz and the unit of the rise time is seconds. The next point is the useful statements about the feedback in control system are. So now we'll discuss some important points regarding the feedback in a control system. Feedback can improve the stability or to be harmful to stability. Basically, feedback can improve the stability or it can be very harmful to the stability. Means if it is not applied properly. Means by using the feedback we can improve the stability or we can decrease the stability also. Feedback does not guarantee that it always improves stability. So feedback does not guarantee that it is always going to improve the stability. In many situations, the feedback can reduce the effect of noise and disturbance on the system performance. And I have already told you, suppose if you are going to use a negative feedback, then the overall noise is going to get reduces and the disturbance of the system is also going to get reduces. In general, the sensitivity of system gain of a feedback system to a parameter variations depend on where the parameter is located. Because in general, the sensitivity of the system gain of a feedback system to a parameter variations depends on where the parameter is located. So I've already told you in the case of negative feedback system, the parameter variations of the feedback element is more when compared to parameter variations of the planned planned one. So when compared to, so feedback has a more parameter variations when compared to the planned G of S. So these things always you have to keep in your mind. So feedback can improve the stability, it can also decrease the stability if you are not going to apply properly. So basically, if you are going to use a negative feedback system, the noise is also going to get reduced and disturbance is also going to get reduced. And whatever the sensitivity of the system is basically depends on the parameter where it is located. And I've already told you in the case of negative feedback system, the parameter variations of the H of S is more when compared to the parameter variations of G of S. So we can say feedback can improve stability or can be harmful to stability if it is not applied properly. feedback does not guarantee that it is going to always improve the stability. In many situations, the feedback can reduce the effect of noise as well as disturbance on the system performance. In general, the sensitivity of the system gain of feedback system to parameter variations depends on where the parameter is located. So finally, I can say, basically, feedback can improve the stability or it can decrease the stability if it is not applied properly. So feedback is not going to guarantee that it is always going to improve the stability. So if you are going to apply the negative feedback, the effect of noise is going to be reduced and also the disturbance of the system and the system performance is also going to be reduced. And the sensitivity of the variation of the output is dependent upon the parameter of the parameter variation where it is located. So in the case of negative feedback system, the sensitivity of the output when the parameter variations of H of S is more when compared to the sensitivity of the output when the parameter variations in G of S. So this one I already told you. Next point is, by using the feedback in control systems, the sensitivity to parameter variations is improved. This is achieved at the cost of loss of system gain. By using feedback in control systems, the sensitivity to parameter variations is improved. This is achieved at the cost of loss of system gain. So basically, if you see the open loop transfer function, what is going to happen? In the case of open loop transfer function, gain is higher. Gain is higher. And also, we can say, sensitivity is also higher. Sensitivity is higher means we can say, sensitivity is higher means simply we can say, as there is a huge amount of variation, suppose if there is any variation in the parameter, so the output is also going to get very, very higher. In the case of closed loop transfer function, what is going to happen? Gain is also going to get decreased and the sensitivity is also going to get decreased. Decrease means we can say it is improved. It is improved. Improved means we can say now, even though there is a variations in the elements, but still the output is going to very, very little. The sensitivity is very, very less. Even though there is a variations in the parameters of the feedback element or the fraud element, but still the output is going to be very lesser because of the feedback. So sensitivity is decreasing means we say it is improved. So therefore, by using feedback in control systems, the sensitivity to parameter variations is improved. This is achieved at the cost of loss of system gain. So in simple words, I can say like this. In the case of open loop transfer function, gain is very higher and the sensitivity is also very higher means if there is any parameter variations in G of S in the fault path element, the output is going to be very, very larger. Whereas in the case of closed loop transfer function like negative feedback, the overall gain is going to get decreases, but still the sensitivity is also going to get decreased. So because of this decrease means sensitivity decreasing means it is improved. So now what is going to happen? If the gain is going to see basically, even though there is a variations in the feedback path element or the fault path element, but still the variation in the output is very lesser. So we can say the sensitivity is improved. Sensitivity is improved. So why it is like this? Because the gain is also decreased. So now the next point is the advantages of the closed loop negative feedback control systems over open loop systems. So now we'll discuss some important advantages of the closed loop negative feedback control systems over the open loop systems. So now we'll discuss some advantages of the closed loop negative feedback control systems over the open loop systems. The overall reliability of the closed loop system is more than that of the open loop system. So the overall reliability of the closed loop system is more when compared to open loop system. The transient response in a closed loop system decays more quickly than in open loop system. In an open loop system, closing of the closed loop decreases the overall gain of the system. In the closed loop system, the effect of variation of the component parameters on its performance is reduced. So basically we are going to compare the negative feedback system as well as the open loop system. So we are going to basically compare the negative feedback system over the open loop system. So the overall reliability of the closed loop system is more when compared to the overall reliability of the open loop systems. And the transient response in a closed loop system decays more when compared to open loop system. So transient response in the closed loop system is going to decay very more when compared to the less time it's going to decay when compared to open loop systems. In an open loop system, closing of the loop is going to decrease the overall gain of the system because in the case of negative feedback, the gain is going to get decreased. In the closed loop system, the effect of variation of component parameters on its performance is reduced. So in the case of closed loop system, the effect of variation of the component parameters on its performance is reduced. And what I told you, basically whenever the any parameters are going to get vary, in the case of negative feedback system, the threshold is very less, so less amount of variation in the output. So in the closed loop system, the effect of variations of the component parameters on its performance is reduced. So finally, I can say the advantage of the closed loop negative feedback control system or the open loop systems are the overall reliability of the closed loop system is more when compared to the open loop system, and the transient response in a closed loop system is going to decay more quickly than in the open loop systems. And in an open loop systems, closing of the loop is going to decrease the overall gain of the system. Simply we can say the gain of the closed negative feedback closed loop system is very lesser when compared to the gain of the open loop system. See, in the closed loop system, the effect of the variation of the components parameters on its performance is reduced, because even though there is a variations in the h of s and the g of s, still the output is going to be very lesser. So its effect is very less. The next point is, in the control system, excessive bandwidth is not employed because noise is proportional to bandwidth. And what I told you, as the bandwidth increases, the noise is also going to get increases. So that is the reason in the case of control systems, always we prefer the less bandwidth. In the control system, excessive bandwidth is not employed because noise is proportional to bandwidth. In the case of control systems, always we prefer to choose only low bandwidth only. Low bandwidth only we are going to prefer in the case of control systems, because as the bandwidth increases, the noise is also going to get increases. So more amount of noise is going to get added to the system, and the system performance is going to get degrade. That is the reason always we prefer to choose the low bandwidth. So therefore we can say in the case of control systems, always we prefer to use only low bandwidth because noise is proportional to bandwidth. As the bandwidth increases, more and more noise is going to get added to the control system, so its performance is going to get affected. So therefore, finally I can say, in control systems, excessive bandwidth is not employed because noise is proportional to bandwidth. It simply means that, suppose in the case of control system, if you are using the high bandwidth, is what is going to happen? As the noise is taken proportional to bandwidth, so more is the bandwidth, more is the noise is going to get added, and the system performance is going to get decreased. That is the reason we always, in the case of control system, always we prefer to choose the low bandwidth only. So this is some important point. Now we are going to discuss the another point. So listen carefully. The open loop system is inaccurate and also unreliable due to the internal disturbances and the lack of adequate calibration. So this point I have already told you. Basically, open loop system is inaccurate and also unreliable due to the internal disturbance and also lack of the adequate calibration. So basically, what is going to happen in the case of open loop system, as there is no feedback, so definitely whenever any disturbance are going to get are produced in the system, then definitely the output is going to get changes from the desired output. So we can say this is said to be inaccurate system and also unreliable, which we are not sure whether the output that we are going to get is desirable or not. So due to internal disturbances as well as due to external disturbances, we can say the open system is inaccurate as well as unreliable, and also it is a lack of adequate calibration. So we can say the open system is inaccurate and also unreliable due to the internal disturbances as well as the lack of adequate calibration. The next point is the examples of the open loop systems are the traffic light, washing machine, and the bread toaster. So the basically open loop system is there is no feedback. So the best examples of the open loop systems are the traffic light. So you can see traffic light. Basically, this traffic light are going to work on the principle of timing. So they don't know whether in a given line the vehicles are more or not. It doesn't go into measure. It only goes in the principle of time. So for each and every road, it is going to give a time of around 30 seconds or 60 seconds. Only that it is going to give, but it doesn't know whether in which line there is a heavy vehicles are there, so that I need to give more amount of time for this one. So that is not there. If for each and every road, irrespective of the vehicles are present, it is always going to give the same amount of time. So this is the example of open loop system. Whereas the washing machine also. See, for a washing machine, we are going to keep the clothes in the washing machine. So we are going to use some time for it. So until that time only it is going to rotate in order to make the things clean. It doesn't know whether in that given time, whether the clothes are fully washed or not. It doesn't know. It only works for the given amount of time. So if you set the time, it is going to work up to the time, irrespective whether the clothes are washed properly or not properly. Bread toaster means we can say here. Suppose if you went to any shop and if you ordered any samosa, you want the samosa to be very hot, so definitely is going to keep in the bread toaster so that it will become very hot. Suppose if you keep for more amount of time, it will become black in color. But if you keep very less amount of time, it will not get heated. So it depends on the customer. It depends upon the customer for how much amount of time he need to keep. So that system will never tell when to remove or when not to remove. It is a responsibility of the customer. You have to take the break whenever it is, whenever if you see anything, what is going to get happen. So these are called as open loop systems because these are not, it is the customer has to take care of these things. It doesn't know regarding everything is happening or not. So these are the best examples of the open loop systems, which are the traffic light, washing machine, as well as the bread toaster. So now the next point is the sensitivity of M of s with respect to G of s. I have already told you its value is equal to 1 by 1 plus G of s H of s. So if we substitute s is equal to j omega, if omega is not mentioned, then by default we have to use omega is equal to 0. So I have already told you s is always equal to j into omega. Suppose if omega is not mentioned, then by default we have to use omega is equal to 0. So this is a statement always you have to keep in mind. So always you have to keep s is equal to j omega. Suppose if omega is not mentioned, then by default we have to always use omega is equal to 0. So therefore we can say the sensitivity of M of s with respect to G of s is equal to 1 by 1 plus G of s H of s, and s is always equal to j into omega. So if omega is not mentioned, then by default we have to use omega is equal to 0. So sensitivity of M of s with respect to G of s is equal to 1 by 1 plus G of s H of s, where s is equal to j omega. Suppose if omega is not mentioned, then by default we have to use omega is equal to 0. Suppose in the exam, in the question they have not mentioned what's the value of omega. So by default we have to use its value is equal to 0. So we can say the sensitivity of M of s with respect to G of s is equal to 1 by 1 plus G of s H of s, whereas s is equal to j omega. So if omega is not mentioned, then by default we have to use omega is equal to 0. The next examples is the example of the closed loop systems are, which are the toilet flush tank, air conditioning in air, air conditioning in car, and autopilot system, as well as the DC motor speed control. These are the best examples of the closed loop system. Toilet flush means carefully. Suppose if you went into the modern toilet flush, definitely whenever you are going to press that flush, the water which is going to store there, it is going to come outward. Again, it is going to get filled up to a certain level. So this is called a closed loop system. So therefore, whenever you flush the tank, water is going to come outward, and automatically the water manually you don't have to pour the water. Everything will be automatically in that case. So this is the best example of the closed loop system. So therefore, we can say whenever you flush the tank, the water is going to come outward, and automatically the water is going to come inward. So therefore, we can say that it is the best example of the closed loop system. So this is we can say that the toilet flush tank. So this toilet flush tank is the best example of the closed loop control system. Now next thing is air conditioning in car. See, air conditioning in car also is the same thing as the closed loop system, because whenever you on the AC, the room is going to get very cool. The room is going to become very cool, but after a certain limit, the cooling is going to become strong, because it is a closed loop system. So therefore, it is going to know as the temperature is desired value is obtained. So now it's time for stopping. So that is the air conditioning in a car. So this is the basic example of the best examples of closed loop systems, as well as the autopilot system also. Autopilot system is autopilot system is there is no person. See, the man is not there in order to control the pilot. So automatically we can basically automatically with the help of control systems we can make the car to move without any person. That is called as a closed loop system. And the DC motor speed control is also a closed loop system, because the DC motor control, just now we have seen there is a closed loop system. Whenever you go for the armature control, definitely there is a feedback. But if you go for the field control, then there is no feedback. But if you go for the armature control, yes, there is a feedback from output to input. So these things always you have to keep in your mind. The next one is the value of the closed DC gain is smaller than the value of the open loop DC gain. The value of the closed loop DC gain is smaller than the value of the open loop DC gain. I've already told you the DC gain of the open loop system is very, very higher, whereas the closed loop gain of the closed loop gain is basically very, very less. So the value of the closed loop DC gain is smaller when compared to the value of the open loop DC gain. So what I am trying to tell you is very, very simple. So see here, I can say, suppose for the closed loop, so closed loop transfer function, its DC gain is always lesser than the closed loop, open loop transfer function DC gain. So DC gain means t is equal to 0. So whatever the gain that we are going to get, this is called as the DC gain for the closed loop as well as the open loop. So therefore we can say, finally, the value of the closed loop DC gain is always smaller than the value of the open loop DC gain. DC gain means substitute S is equal to 0. So the transfer function, if we substitute S is equal to 0, we are going to get the DC gain. So we can say for the closed loop transfer function, if you keep S is equal to 0, we are going to get the DC gain for closed loop system. And if for the open loop transfer function, if you substitute S is equal to 0, then we are going to get the DC gain for the open loop transfer function. If you are going to compare these two gains, we can say the closed loop transfer function DC gain is always lesser than the open loop transfer function DC gain. So this point always you have to keep in your mind. The next one is the gears are analogous to electrical transformers. So whenever you are going to compare the electrical system as well as the mechanical system, electrical transformers are analogous to gears. So the mechanical system gears, the electrical systems electrical transformer, both these things are same. In the case of electrical transformers, we can say if you are going to increase the voltage, then the current is going to get decreased. If you are going to decrease the voltage, means current is going to get increased. Similarly, in the case of gears, also, if you are going to increase the speed, then what is going to happen? I have already told you, work is equal to torque into displacement. Work is equal to torque into displacement. So, as the torque decreases, then the speed will increase. As the torque increases, the speed will decrease, because the torque is always equal to constant. So this one I have already told you. So therefore, less is the torque, more is the speed. More is the torque, less is the speed. So this point I have already told you in the case of the gears. So therefore, if you are going to compare the electrical systems as well as mechanical systems, electrical transformers are analogous to gears. The next point is, while deriving the transfer function of a linear element, initial conditions are always assumed to be 0 and the element is assumed to be not loaded. So we can say, whenever you are going to derive the transfer function of a linear element, the initial conditions are always assumed to be 0 and as well as the element is assumed to be not loaded. So this one I have already told you. While we are going to derive the transfer function of a linear element, the initial conditions are always assumed to be 0 and the element is assumed to be not loaded. So therefore we can say, in simple words I can say like this. Basically, whenever you are going to figure out the transfer function of any linear element, always the initial conditions are always assumed to be 0 and also we have to assume that the element is not loaded. So these things always you have to keep in your mind whenever you are going to figure out the transfer function of a linear element. While deriving the transfer function of a linear element, the initial conditions are always assumed to be 0 as well as the element is assumed to be not loaded. The natural time constants of the response of the system are T1 and T2. The natural time constants of the response of the system are T1 and T2. So you can see the transfer function is equal to C of S by R of S is equal to, it is a ratio of the numerator by denominator. So try to write in the time constant format. So this T1 and T2. So these are basically the poles. These poles are called as the natural time constants. So listen carefully. These T1 and T2 are called as the natural time constants of the response of the system. See, whatever the poles, the amount of the, so we can say, basically, so these time constants T1 and T2 are called as the natural time constants of the response of the system. Suppose for a given system, the transfer function C of S by R of S is a ratio of numerator by denominator. So these denominator time constants are called as the natural time constants of the response of the system, which are T1 and T2. So this point always you have to keep in mind. suppose if you have figured out the transfer function, if you figure out the transfer function of any system, and if you are going to get in this format, which is C of S by R of S is equal to ratio of the numerator by denominator, and denominator in the case of time constant formats, and P1 and P2 are called as the natural time constants of the response of the system. So now we'll discuss another point, which is natural time constants of the response depends only on the poles of the system transfer function. As I already told you, just now we have seen the natural time constants of the response, they are going to depend only on the poles of the transfer function of the system. So what are the natural time constants of the response? They are going to depend only on the poles of the system transfer function. So we can say what are the natural time constants of the response? They are going to depend upon the poles of the transfer function, system transfer function. So we can say the natural time constants of the response, they are going to purely depend only on the poles of the system transfer function. So we can say the natural time constants of the response, they are going to purely depend only on the poles of the system transfer function. Now we will discuss another point, which is in the transfer function, the initial conditions are 0. I have already told you while you are going to figure out the transfer function, we always assume that the initial conditions are 0. So output 1 by input 1, it indicates that for all other inputs and outputs are considered 0 or just removed. So basically, suppose in the given system we have multiple inputs and multiple outputs. So out of these multiple inputs and multiple output, I want to find what is the ratio of the output 1 by input 1. Then remaining all other inputs, I am going to assume it is 0. Are the remaining all other outputs, I am going to assume it is 0. 0 means we can say simply they are removed also. Therefore, we can say in the case of transfer function, always the initial conditions are always assumed to be 0. And in the case of multiple input and multiple output system, whenever you are doing a ratio of a given output by given input, then all other inputs are assumed to be 0 and all other inputs are also assumed to be 0. 0 means we can say they are just removed. So therefore we can say in the case of transfer function, whenever always we are going to assume the initial conditions are 0 whenever you are going to figure out the transfer function. And for a multiple input and multiple output, if you are specifically finding the ratio of a particular output by particular input, then all other inputs are assumed to be 0 and all other inputs are assumed to be 0. 0 means they are removed. So now the next point is transfer function is defined for linear systems. So superposition principle is applicable. So basically the transfer function is basically applied only for, it is defined only for the linear systems. So this is a point always applicable in mind. The transfer function is basically, it is defined only for the linear systems but not for the non-linear system. So based on this principle only we can say, so superposition principle is also applicable for the transfer function. So this one always you have to keep in mind. Suppose for a given system, so let me assume a given system is a linear system. It has multiple input and multiple output. Then I want to find what is the transfer function of this whole system. Then what we are going to do? Then we are going to find in what is the output because of input 1 and what is the output because of the input. Then if it is a solution of these two things, then we are going to get the overall output. So listen carefully. Suppose let me take some system is having multiple inputs and only one output. So now I want to find what's the overall transfer function. Overall transfer function, it is nothing but transfer function of output with respect to input 1 plus transfer function of output with respect to input 2, and it goes on up to total number of inputs. So we can say as a transfer function is defined only for linear system, so therefore the superposition principle is also applicable. So this one always you have to keep in mind. As the transfer function is defined only for the linear systems, so superposition principle is also applicable only for the transfer functions. So what I am trying to use in very simple words. So now suppose let me take a linear system. It is having multiple input and only single output. Then I want to know what is the overall transfer function of the system I want to find. Overall transfer function, it is nothing but the transfer function of output with respect to input 1 plus the transfer function of output with respect to input 2, and it goes on up to total number of n number of inputs. So this is what I am trying to tell you. Suppose if you want to write it if you want to write in terms of mathematically, the overall transfer function is equal to a transfer function of output with respect to input 1 plus a transfer function of output with respect to input 2 and it goes some up to n number of inputs. This is the meaning of this one. So transfer function is basically defined only for the linear systems. So superposition principle is also applicable for these transfer functions. The next point is signal flow graphs can be used for block diagram reduction. Signal flow graphs can be used for block diagram reduction of linear control systems because signal flow graph is a graphical representation of the variables representing the outputs of the various blocks of the control system. Signal flow graph can be used for block diagram reduction of the linear control systems because signal flow graph is a graphical representation of the variables representing the outputs of the various blocks of the control systems. So we can say signal flow graph is a graphical representation of the block diagrams. So by this, very simply, we can basically draw the signal flow graph of the block diagram by using the summing points as the nodes as well as the takeover points as nodes. Then we are going to represent this one, and with the help of Mason's case formula, we can easily figure out the transfer function. So signal flow graphs can be used for the block diagram reduction of the linear control systems because signal flow graph is a graphical representation for the variables representing the outputs of the various blocks of the control system. So in simple words, I can say like this. Basically, suppose if you take a block diagram, it's very complex. So with the help of signal flow graph, what we are going to do is, we are going to simplify this one by assuming the summing points as the nodes as well as the takeoff points as the nodes. Then we can easily draw the block diagram, the signal flow graph. With the help of Mason's formula, we can easily figure out the transfer function in a very easier manner. So we can say the signal flow graphs can be used for block diagram reduction of the linear control systems because signal flow graph is a graphical representation for the variables representing the outputs of the various blocks of the given control system. The next point is, in systems where the low frequency magnitude is 0 dB on the Bode diagram, the bandwidth is measured at the -3 dB frequency. In systems where the low frequency magnitude is 0 dB on the Bode diagram, the bandwidth is measured at the -3 dB frequency. So basically, suppose, what is the meaning of bandwidth? Suppose if you draw the Bode diagram, suppose if you got like this. So let me assume this is a 0 dB and this is -3 dB. So this is a -3 dB. Then what is the range of this frequency? So this overall frequency range is called as the bandwidth. So therefore we can say this overall range is called as the bandwidth. So therefore we can say whenever you are going to draw the Bode magnitude plot, and if the magnitude plot is going from 0 dB to -3 dB, this range of frequency is called as the bandwidth. This overall is called as the bandwidth. So in systems where the low frequency magnitude is 0 dB on the Bode diagram, the bandwidth is measured at the -3 dB frequency. So at -3 dB, just try to figure out this frequency, and its total range is called as the bandwidth. So therefore we can say in systems where the low frequency magnitude is 0 dB on the Bode diagram, and the bandwidth is measured at the -3 dB frequency. So you can see basically if you are going to draw the Bode magnitude plot, suppose if you are going to get in this figure like this, at low frequencies its value 0 dB, and if this decrease at this particular frequency, the Bode magnitude plot we are going to get -3 dB. So this range of frequency is called as the bandwidth. The next point is the bandwidth of the closed loop control system is a measurement of the range of fidelity of the response of the system. The bandwidth of the closed loop control system is a measurement of the range of the fidelity of the response of the system. So what is the meaning of the fidelity of the response of the system is the response of the system can lie in this range of frequencies. So basically the bandwidth of the closed loop control system means the output can have a frequency variation from some 0 to the bandwidth frequency of the cutoff frequency. Also we can say this is the bandwidth frequency. So this is a range of the frequencies which are possible with the help of the particular closed loop control system. So the bandwidth of the closed loop control system is a measurement of the range of the fidelity of the response of the system. So what I am trying to tell you is very simple. Suppose if you take a closed loop control system, and you have measured the bandwidth of the closed loop system some value, then if you are going to find it, if you are going to measure, if suppose for a given system, if you know the output can have a range of frequencies from 0 to the particular bandwidth frequency or the cutoff frequency. So only this range is possible. So that is the meaning of this statement. The bandwidth of the closed loop control system is a measurement of the range of the fidelity of the response of the system. The bandwidth of the closed loop control system is a measurement of the range of the fidelity of the response of the system. The next point is the speed of response to a step input is proportional to the bandwidth. So this one always you have to keep in your mind. The speed of response to a step input is always proportional to the bandwidth. So I already told you, see, whatever the speed of response to a step input is always proportional to the bandwidth. So this is a very, very important statement. Always you have to keep in your mind, which is, you can say, the speed of response to a step input is always proportional to the bandwidth. As the bandwidth increases, the speed of the response to a particular step input is also going to get increased. So I can write like this. So basically we can say the speed of the step response, the speed of the step response, you can say the speed of a step response means S of t is always directly proportional to bandwidth of the system. The speed of the response to a step input is always proportional to the bandwidth of the system. So we can say the speed of the response of a step input is always directly proportional to bandwidth of the system. As the bandwidth increases, the speed of the response of the step input or step response is always going to get increased. If the bandwidth increases means the speed of the step response is going to get decreased. So always you have to remember, which is the step response speed. The speed of the step response is always directly proportional to bandwidth. As the bandwidth increases, the speed of the step response increases. As the bandwidth decreases, the speed of the step response will decrease. So this point always you have to keep in your mind. So as the bandwidth increases, the speed of the step response will increase. As the bandwidth decreases, the speed of the step response will decrease. So this point always you have to keep in your mind. So therefore we can say, as the bandwidth increases, the speed of the step response will increase. As the bandwidth decreases, the speed of the step response will decrease.